Okay, so welcome to week 9 of the Introduction to Semiconductor Fundamentals. Uh, I am Shazan Bhatt and I'm a direct PhD student at IIT Bombay in Electrical Engineering Department. So, as per the, I should say, ritual we have been following from a couple of weeks, I should say 9 weeks. Uh, we are currently landed at this particular topic called as metal oxide semiconductor field effect transistors. So that's what MOSFET stands for. And so we have gone through a couple of maybe rigorous sessions and assignment sessions and finally landed up at this particular topic. So now we are going to see where all of those concepts are going to again apply, starting from the basic electrostatics in week 1, week 2, and then you studied about the PN junctions, you studied about the you studied about the MOS junctions, metal semiconductor junctions, and MOS capacitors as well. So let's briefly discuss about what we have currently, where we are currently, and then we will basically study about we will basically solve the assignment problems. Okay, so in the previous session, we actually talked about something called as metal oxide semiconductor, which is the MOS, or what you call as MOS capacitor. So it is a capacitor because it acts like a capacitor. There are just like a capacitor, there are two plates separated by some dielectric between it, and two plates which are charged plates are separated by certain dielectric, and you can obtain the capacitance as something like this, which is epsilon A over D from the basic electrostatics. But the assumption here is that we have the electric field something like this, and you totally ignore these electric fields here, which are something called as fringing fields, fringing electric fields. While doing the derivation, you don't consider these fringing fields at all. So for a first order approximation, we neglect these fringing fields, which are basically coming out from the edges of those plates. So that is the basics of the capacitor. And in the MOS capacitor, you showed that if you have a, let's say, a metallic layer, and if you have an oxide layer in between of the metallic layer and the semiconducting layer, let's say this is a p-type semiconductor, then you have three regions, something called as accumulation region, you have the depletion region, and you have the inversion region. Okay, so these three regions basically govern the operation of a MOS capacitor and what type of charges will be accumulated at this particular place, whether these will be electrons, whether it will be holes, or whether it will be just ions, immobile ions. It is just governed by the voltage you apply at this particular terminal. Okay, so the voltage applied at this particular terminal, something called as VG gate voltage. This is a small signal voltage, which is an AC, let's say, but it governs the electrostatics of the channel of the region, charged region, which is this region formed beneath the oxide layer. So now the question was again back in the previous lecture that where are we going to use this channel? So we have just created the channel. Now what we are going to do with this channel? That is the main question. So what I showed you in the previous lecture is that if you have this MOS capacitor structure, you have this MOS capacitor. Let me remove these. And now what you can do basically is that you are going to use these particular electrons which are present in this channel, which are present here, whether they are electrons or holes that we are going to see, but you have created this inversion charge or any sort of charge below the oxide for it to flow. You have not created it to just stay at this particular location. Okay, that might have other applications, but what you are going to do with it? Now you have to extract these charges, or you have to make these charges flow. Now for that sake, you bring in just two terminals. I should say these are just two terminals you bring into these devices to make it something called as metal oxide semiconductor field effect transistor. Right now, it's just metal oxide semiconductor, a capacitor, where this is metallic plate, where this is semiconducting plate, and in between there is an oxide. But now what we do is that we bring in a region here, and we bring in another region here at this position. Okay, and this region is, let me just draw it, this region and this region acts like almost like a connecting probes. So these regions are something called as, this region is called as source region, and this region is called as drain region. And you surrounded something like this, and you get a structure which is the MOSFET structure. Okay. Now what happens if, let's say, this is a p-type semiconductor, bulk bulk semiconductor. Let's say this overall is p-type. Let me remove this now. This overall is p-type, something called as p-type substrate, p-type silicon. That means it's doped with acceptor type impurities. That means it has positive charge and a hole, excess holes. So what you do is that you make these regions, which are source and drain regions, as highly doped regions of the charge, of the same charge type, the same charge that is going to flow at this particular position. You know, for if you have a p-type semiconductor, if you have a p-type silicon or a p-type substrate, in case of a MOS, in case of a MOS, then you know upon inversion, when you invert the channel, you know that electrons are going to be present at the oxide semiconductor interface. You remember about applying a, I should say, a positive voltage on the gate side, a positive voltage on the gate side VG, and a negative voltage on the semiconductor side. You bend the band something like this. Okay, where this is the Fermi level, and this Fermi level almost touches this particular band here, and you know that there are excess, now this particular channel has been inverted here. Now there are more electrons present here, electrons. Okay, that means this particular region has been inverted. Earlier it used to be p-type, but now it's n-type. So these electrons, let me just complete this. So these electrons are present at this particular location here, at this particular location here. Okay. So now what we are going to do, we are going to dope the source and drain regions with the same type of, I should say, with the same type of carrier which is present, which we are going to, which we are going to, I should say, induce in the channel. Let's say if there are electrons induced in this region, if there are electrons induced in this region by the inversion of the channel, the p-type substrate has been inverted at this particular region by application of the gate voltage, which is greater than the threshold voltage. That you also know, the threshold voltage concept. You know that this particular, you know, the CV characteristics of the, of this particular device looks something like this. This is under low frequency characteristics, where this is the accumulation, where this is the depletion capacitance, and this is the inversion capacitance, and this particular voltage is the threshold voltage. Okay. So there are these three regions. This is the depletion region, this is the overall inversion region at low frequency of the applied bias, and this is the accumulation region. Okay, so now beyond this, beyond the threshold voltage, you have the inverted region which contains excess number of electrons. So now what you do is that you dope this particular, or you, I should say, you take these N and source and drain regions as the same type of semiconductor having the same carriers as that present in the channel, as that what you have induced. If you have induced electrons here, you take it as N plus. If you have induced holes here, you take it as these as P plus. Then this substrate has to be N type. Okay, that you should always keep in mind. If this substrate is N type, these regions has to be P type. If this substrate is P type, these regions have to be N type. That is the overall fundamental, because for the P type, for the p-type substrate, electrons will be induced here. For the n-type substrate, holes will be induced here. Just keep this in mind always. That is the difference between a p-type and an n-type MOSFET, and particularly in this particular scenario. So we are right now studying here a p-type semiconductor and a p-type this device, or this is a p-type substrate, and this is something called as NMOS. Why NMOS? Because N stands for electrons, are electrons in the channel. Electrons in the channel. What is channel? This region is the channel where you have inverted the region to form the electrons. Okay, that is, this is called as channel. This is called as channel. channel of electrons. Okay, so now you have these n plus regions. And what are these n plus regions? These are highly doped regions, highly doped regions of or highly doped n-type regions. That means you have it highly doped it with n-type impurities. That means negative ions and excess electrons are present in this region. There's a negative ion and excess electron, negative ion and excess electron. Just like in a p-n junction. In a p-n junction, you had negative ion and excess electrons, positive ion and excess holes. So you have here, uh, I should say, oh no, I'm saying the opposite. So in P and N type, you have positive ions and excess electrons. Here you have negative ions and excess holes. So here you have and D type impurity, which is the donor type impurity. That means positive ion and excess electrons. This is positive ion and excess electrons, positive ion and excess electrons. So that's why you have a depletion region formed here between P and N type. Okay, so that is the concept I want to give you. So if you take this MOSFET device now, we are just studying about the device right now. We are not even applying any voltage, just studying about the device. Let me duplicate it. If oh, why is it behaving weirdly? So let me duplicate it, keep it here. Let me rub this thing also. So what happens basically is that you have these highly doped regions on these particular sites. Okay, now the same scenario you have to apply here what we are doing in the PN junction case. Now if you want to visualize this in three dimension, this is basically something like this. If I rub these particular things, it is something like this. Okay, where this hole is the metal. This is the deposited metal layer. This is actually how it is made. And this region is the drain region. This region is the source region. And you connect the battery terminals, whatever the terminals you want, you connect them here. And this is the gate terminal. This is VG, this is VD, this is VS, and you have another terminal which you mostly ground. Actually, it's not grounded in the transistors, but for the sake of simplicity, right now we consider this is called as body. So this is called as body terminal VB. So this is usually grounded with respect to and everything is grounded with respect to the body basically. Okay, so these are the terminals of the MOSFET. So this is the three-dimensional layout of a MOSFET. So whatever you study is a cross section of this layout. Cross section means you actually I should say dissect this region here in a plane. This plane you study. Okay, you dissect this MOSFET, and that is what you draw it in a. This is the front view of MOSFET. Whatever you are seeing from this is the front view you see, and this is the top view of the MOSFET. Top view. Okay, so it's basically a three-dimensional structure where you have to now consider the three-dimensional electrostatics. These regions basically also are present here. Okay, so this is the metal overall, this is oxide, and this is the semiconductor. So now you have to be careful, very careful in understanding the electrostatics of this particular structure. Now, moving on to the next thing, what what we have is there are there are two types of these MOSFETs which are usually found, which we usually make. Two types of MOSFETs. Maybe you might have studied about, or you can look it in the book itself, but I don't want to give you the same thing which is written in the book. I don't want to discuss those same things which professor has taught, because it's of no use to you to discuss the same kind of things in this session. So I want to discuss some different things. Maybe this professor might have already discussed about these things, about the enhancement type MOSFET and the depletion type MOSFET. And the just simple distinction between these two types is that in the depletion type MOSFET, you already have a channel. Already channel is present. What channel? Just these particular electrons or the holes are already present there. Okay. And what happens is that you have to apply the opposite voltage to repel those holes away from the channel to make it off. So that's why this type of MOSFET is called as normally this type of MOSFET is called as normally on type MOSFET. It's usually on, so that's why it's not mostly used. Okay, in some applications it's used, but most of the time it's not used because it's usually on. You have to apply the voltage to turn it off. So that results in a kind of I should say continuous power management issues because it's almost all the time on. You just have to apply the voltage to turn it off. Just like for example, if you have this N plus source, this is N plus drain, this is oxide, this is the metal, then you will have electrons here already after you have fabricated it, even if you don't have applied any voltage. So what you do, you apply a negative voltage here with respect to this. Okay, with respect to this, you apply a negative voltage here. Negative voltage repels these electrons, and that you have seen. It's a field effect. Whatever the field, because you have induced negative charges here, that is going to repel those electrons away from the channel in a layman sense. Okay, that's what happens in the MOS capacitor even. So what it does is that it brings these electrons away from the channel, and you no longer have the channel, and it turns off. So by application of this voltage, you have turned the device off. Otherwise, it was already on. You could have just connected these terminals, let's say positive terminal and let's say negative terminal. You could have connected these source and drain terminals, and the current would have started to flow without even applying the gate voltage. Gate voltage is necessary. That means you would have got drain to source current would have been non-zero at Vg equals to 0. That is the depletion type MOSFET. If you apply the drain to source voltage, if VDS is non-zero, IDS will be non-zero and Vg will be 0 under these conditions. Even if you don't have any gate voltage applied, you will have the conduction. But you apply the gate voltage, if you apply the gate voltage as negative and you have VDS as some let's say non-zero value, then you can make the IDS equals to 0. You can make this particular drain to source current as 0. That is the functioning of a depletion type MOSFET. On the other hand, enhancement type MOSFET is this is the off type MOSFET, but what we usually use in the CMOS logic circuits, that is mostly used because in this type of MOSFET, the channel is not present itself, and we have to induce the channel by applying the voltage, just like in p-type semiconductor or something called as NMOS, which is a structure like this MOS, where this is p-type. You know that you have to apply certain positive voltage here and negative voltage here in order to induce the channel, in order to make the electrons, excess electrons present here at this region. Okay, that you have created by applying gate voltage. They are not inherently present. Okay, so what you do here is that you can apply Vg to turn it on and remove Vg to turn it off. So this is the usual scenario what we want. Okay, we want to apply the voltage so that it should turn on. Turn on means these electrons would be present. These electrons would be present in the channel when we apply the gate voltage in the enhancement type MOSFET. So that is the broader classification of these depletion and enhancement type MOSFETs. Now the question is, where do these electrons come from, which are already present in the channel? It depends upon the different factors. It depends upon the metal and semiconductor work function difference. It depends upon many internal device properties or the material properties used that creates a already present, uh, I should say, channel inside this particular MOSFET. Okay, so there are certain device characteristics or the material properties which can inherently create this channel. Just like you knew that if you have a CV characteristics, CV characteristics look something like this. Okay, but if you go on maybe change, this is for the ideal scenario where let's say you have the flat band voltage which depends upon the work function difference of the metal and semiconductor, and it depends upon the some fixed charge inside the oxide. So this means that if let's say you have a flat band voltage to be equivalent to zero, what does it mean? What does it mean? It means that all the bands are flat. You don't need to apply any voltage to make the bands flat. Okay, all the bands are flat under equilibrium. And if you have flat band voltage to be non-zero, that means you have to apply some voltage to make the bands flat. Why the flat band voltage will be non-zero? Because of this work function difference, because of some fixed charges. So these particular non-idealities play a crucial role in determining whether the transistor is a enhancement type transistor or a depletion type transistor. So here is a three-dimensional view of a transistor basically, which has been taken from this particular reference. Maybe professor has also referred to it, and that's what actually I have shown here. This is the three-dimensional structure I have shown. This is the actual three-dimensional structure. It's the same thing. So now the thing is that you need to basically think it in a three-dimensional aspect here. Now because it's not a two-dimensional device. This particular thing is the channel length. This particular thing is called as gate length. There's a difference. This is the length of the deposited gate over the substrate. Let's say this is the top view. I'm drawing the top view of this. If you are looking, if this is your eye and you are looking at this device from the top, you will see this. This is the top view. You will see this. This is source, this is drain, and this is gate. This is gate. So these are deposited metallic layers over it. As a result, what happens is that this is having some width and this is having some length. Let's call it L drawn as per this particular thing. That means this is the gate length. Okay. And below it will be the channel. If you now look at the front view, that means if you look from this view, which let's say this is your eye, and you are looking from this angle, from this front side, what you are going to see, you are going to see something like this. Let me draw this drawing here. Let me draw this. This is basics from the engineering drawing. Okay, you will see something like this, where this basically is the drain source, this is the drain, this is the gate. This is the oxide first, because you cannot show oxide in the top view. You can only show oxide in the front view, and this is the gate. This is the gate. So this is the gate, this is the source, this is the drain. This is the front view of it. And you see that there are these overlapped regions with the gate. Okay, that makes this particular length, which is the channel length, smaller than that of this length, which is the gate length. So channel length is smaller than the gate length. So the channel which is formed between the source and the drain, where the charges will be present, mobile charges, it may be holes, it may be electrons, depending upon the type of semiconductor. So that channel length is smaller than the gate length. Okay, because the deposited layer over it is usually you cannot control whenever these source and drain regions are made. These are kind of made by, I should say, doping process. These are something called as pockets, highly doped pockets. So they are made by doping process, and doping is I should say, you cannot control it to a very precision level. So whenever you make these regions, those dopants spread. So if let's say this is N plus, this is N plus, that means you have doped it with ND. This is also doped with ND. Those dopants basically spread in a certain particular fashion. It may be Gaussian spread, it may be Lorentzian spread, or uniform spread. Mostly it's Gaussian spread. So that spreads the overall region, these particular regions, to the just little bit below the gate regions also. And because of which you get I should say, overlap between the gate region and the source and drain regions. But there is a clear-cut separation between the source and drain region, something called as channel length. Something called as channel length. And just a matter of fact, this is the channel length which you might have heard people talking about. Maybe people talk about the new mobile phones. Maybe Apple or Mac or Samsung talks about 5 nanometer channel, 10 nanometer channel, which is all just a marketing strategy to lure the patient, to lure these consumers in order to buy new products. So this is basically that particular channel length which those marketing agencies talk about. And they talk about, let's say, 5 nanometer channel or 10 nanometer channel. Basically, it does not necessarily mean that the distance between source and drain is 10 nanometer or 5 nanometer. It's a different strategy. What they basically give you is something called as node length or node. It's a different concept. Let's leave about it. Let's don't think about it. But currently, the channel length is at least 10 nanometer, 10 to 14 nanometers. That means the distance between the source and the drain, this distance approximately 10 nanometer currently which is being used. 10 nanometer means there are, I should say, few lattice cells available between the source and the drain. If you have 10 nanometer, how much is 10 nanometer? You know that 1 nanometer is approximately 10 angstrom. That means 10 nanometer is approximately 100 angstrom. And you know the distance between the two atoms is approximately 5 angstrom. And that means 100 over 5, that gives you 20 atoms. That means there are approximately 20 atoms in a straight line fashion present between the source and the drain. Okay, in a unit cell, approximately. So that is the level of the fabrication which is required. You are playing with atoms. You think about 20 atoms or 30 atoms present between source and drain. Just these number of countable atoms are present. And this is still on a shrinking verge, and people are trying to shrink it down to a single atom or two atoms, which is bizarre. And you cannot, and at that particular scale, you are not, I should say, you don't have to just apply electrostatics, then it goes into the quantum mechanics because of the scale you are talking about. Let's just this just a brief fact about it. So now we have talked about this front view and the top view of the device. Let's do one more thing, is that this is the overall schematic of the MOSFET, which we will be discussing in this particular session now. So this is the overall layout which is showing the exact front view. Now this is the front view of the device. That means you're looking at this device from this particular angle, from this particular view. Now what you have done here is that you first few things to note here. Here you have these regions, N plus regions, highly doped N plus regions, highly doped N plus regions. Because you have doped this region with ND, you have doped this region with ND. These are called as ND, highly doped pockets. And what you now do basically is, you know from your basic p-n junction electrostatics that if this is N plus, this is P region overall. This is P substrate. Okay. What is going to happen is you have now p-n junctions formed. This is N, this is P. This is N, this is P. That means if you draw a p-n junction like this, you have a p-n junction like this here. This is p-n junction 1, this is p-n junction 2. Okay. And now you have to play with these p-n junctions. And this is connected with this thing. These are two p-n junctions inside present it. And most of the time these are reverse biased p-n junctions. So that current should not flow in these directions. We don't want the current to go there. Okay. We want the current to flow just near this region. What I mean to say, let me just take one more page, add page. What I mean to say, if you have this device, you have these highly doped pockets, N plus pocket, N plus pocket, you have the oxide layer, you have the metal layer over it, you have this source region, you have the drain region, and let's take it p-type for now, and this is the body terminal. Right now we are considering most of the time it is grounded currently. Later on you will study what will happen if the body you give some potential to the body terminal also. And you know that for a p-type MOS, for a p-type, if you have a MOS capacitor which is NMOS having a p-type substrate, you apply gate voltage greater than the threshold voltage, which is threshold voltage is mostly positive. You induce the channel, you cause the inversion of the channel. When the inversion happens, you have the excess electrons near channel or near the semiconductor interface oxide semiconductor interface. That means this region. Whenever this particular value is given as a gate voltage, that means you apply positive voltage. All is with respect to the body terminal. You apply a VG which is greater than V threshold. You induce the channel in the region below it. You have the excess electrons near it. Okay, you have the excess electrons near it. Now, what is going to happen? You have to take these electrons out now. You cannot make these electrons to stay there. So for that, you apply another, I should say, bias to this particular terminals, the source and the drain. Okay, what you do is that you connect a negative terminal. Let's say if you connect a negative terminal to this and you connect a positive terminal, you connect a drain voltage like this, you connect a source voltage like this. This is VD, VDS, and this is source voltage with respect to source. Okay. Now you have to think when you applied a negative voltage at the source terminal, electrons are going to go in this direction because negative voltage is going to repel the electrons. A simple basics. Those electrons are going to go here. And here you already have so many number of electrons present that I should say a current is going to flow in the opposite direction of the flow of electrons because electrons are going to flow in this direction and the current is going to flow in this direction, which is called as drain to source current. This is the direction of the current. That is the fundamental thing. Now what you have done is that you have created a pathway of electron flow, and which has what thing has helped you to make this pathway? That is this gate voltage. This is the necessary thing about it. If you don't have gate voltage, you won't have this current flowing. If Vg is 0, IDS will be equivalent to 0. As simple as that. You won't be having electrons. The channel will be highly resistive. There will be no electrons. There will be only, let's consider instead of this, you were having, let's consider you are having VGS less than VTH. Or let's say the MOS capacitor was in depletion region. Depletion region. Depletion region means there are immobile ions. There are immobile ions. Okay. These immobile ions cannot move. So even if you have electrons coming from this region, they will face huge scattering because of the ions, and ions itself are not going to move. So you will be having very, I should say, negligible current flowing through it. And in the opposite case, when if there are holes, you don't have any scenario of flowing the current. So you have to induce the same type of charges here in order to make the current flow, which are the electrons in this case. It can be holes if the substrate is n-type substrate. So let me remove this particular thing here. So you have the electrons flowing in this direction, the current flowing in the opposite direction, which is the drain to source current. Now let's go dig deeper into this particular thing. You know that whenever, let's say, if you go on applying, increasing the, I should say, the drain voltage, what is going to happen? Let's see what is going to happen. Initially, you apply drain to source voltage, few millivolts, and you go on increasing the drain to source voltage. Earlier, we did the same thing in MOS capacitor. But MOS capacitor, we only had one terminal, so we controlled the gate voltage. And we saw that when VGS is less than 0, when VGS is greater than 0, when VGS is greater than VTH, what are the scenarios? you get accumulation, you get depletion region, you get inversion region. So these are all for the MOS capacitor. MOS capacitor. But since the MOS capacitor is a part of MOSFET, this region is a MOS capacitor. This region is a MOS capacitor. Okay, that means this overall scenario is going to be applicable here also. But here in the MOSFET, you are only concerned about this particular region, inversion, because you don't deal about with accumulation and depletion in MOSFET. What you are going to do with it? Because you are not going to make the current flow in the accumulation and depletion region. So you are only concerned about inversion region. Done. That part is done. Okay, so now what is the significance now? Let's dig deeper into the electrostatics. Now we have one more voltage here apart from the gate voltage, which was not present in the MOS capacitor. That voltage is drain to source voltage. This was not in MOS capacitor because this terminal was not in MOS capacitor. It is in MOSFET. Now we want to see what is going to happen if we increase the VDS gradually, increase to few millivolts, then to volts. We are going to see what is going to happen to the device operation. Initially, when the drain to source voltage is small, when the drain to source voltage is, I should say, let's consider a few regions. First of all, let's consider first region when the gate voltage is less than the threshold voltage. In that case, it is simple. You know, even in the MOSFET, these two regions, it is off, and we are considering here the drain to source voltage as zero. Okay. Anyways, it's going to be off. That means no channel formed. Okay. So this is called as something called as subthreshold region. Subthreshold region. Subthreshold means below threshold because VDS is less than threshold voltage. That means it is subthreshold region. Now move on to the next operation. If we make VG greater than V threshold, now inversion is going to happen. Inversion of the channel. Inversion of channel. You will have electrons in the channel, the carriers, because it's p-type. And now you apply small drain to source voltage. Let's say few millivolts, this voltage. You apply small voltage. You have inverted the channel. You have created electron layer here. Now you apply the drain to source voltage. When you apply it, you are going to see that the current increases like this, in this fashion. If this is the drain to source current, this is the drain to source voltage, you see that current increases linearly up to certain point. Up to certain point. What is that point? We will see what is that going to be. Up to certain drain to source voltage point. Okay, this is something called as linear mode. Why? Because the characteristic is linear. It is linearly varying with the drain to source voltage. But note that here you have kept the gate voltage at constant value. As soon as you got the channel to invert, as soon as you got these electrons, that's it. You kept the gate voltage at that particular value. You don't touch the gate voltage anymore. And you get this linear curve. If you find the slope of this curve, what is that going to give you? It's going to give you basically, I should say, y over x is I over VDS. Inverse of the slope is basically going to give you the resistance. The resistance. This will give you conductance. Its inverse will give you resistance. Okay. Resistance is equal to 1 by conductance, which is VDS divided by IDS. That means it's not acting like a normal resistor. It's like Ohm's law. V equals to IR. V equals to IR. Okay. Current is increasing if you are increasing the drain voltage. This is drain voltage, this is drain current, and the resistance is in the channel. There will be resistance in the channel because of scattering events. Now, why is the resistance there? That's a different topic. But definitely, if you pass a current through certain conducting medium, the resistance is always going to be there to the electrons. There is scattering because now electron is going to scatter with itself. Scatter means they are going to randomly move here and there. If let's say this electron is coming from the drain, there are many electrons present in the channel. So we thought that electron will move like this directly into the drain, but electron does not move like this. If electron enters the channel, if this is the channel, electron enters the channel, it goes here, then scatters, then it moves like this, and then it enters into the drain end, and this gives rise to resistance to the flow. Okay, so that is the one main motivation why this channel length, that is the main motivation, this resistance is the main motivation why this channel length is getting reduced in the transistors right now. The thing I discussed to you about 10 nanometer, 5 nanometer, why we are reducing it? Because we want to reduce the resistance. Okay, resistance is equivalent to rho L over A from your 12th class physics. If you reduce this particular thing, you reduce resistance. That's it. That means if you reduce this channel to, let's say, this only now, let's say you have a channel of this length. This is the channel length. Earlier, the channel length was this, let's say. Now the channel length is this region. You will see you will have fewer scattering events. Electron will scatter fewer times. Here, electron will scatter here, fewer scattering events, and it will go into the drain. As you go on reducing the channel length, let's say you have now reduced the channel length. Let's say this is the one end of the channel. Now let's say you have the channel length of this order, in which only one scattering can take place. Electron just scatters once and enters into the drain. This is now drain. So you see that electron is only scattered once. Just one scattering, it enters into the drain. This is something called as ballistic motion. I don't want to go deeper into that. Just want to give you an idea. Ballistic means the, I should say, the distance or the length of the channel is much shorter than the mean free path. Mean free path is the distance between the two collisions of the electrons. Let's say if this is electron, this is electron. If the electron collides with this, it gets randomized to this particular direction. Then before colliding with the other electron, the distance which the electron travels is called as mean free path. And if you make the channel length less than the mean free path, you have something called as ballistic motion. Ballistic means there is no resistance. It will directly go into the drain. As soon as electron will enter the channel, it will directly go into drain. Just like this, just like this. But normally what happens in transistors right now, they are called as diffusive transistors. Diffusive means because they have this type of motion. Electron goes here, scatters, then goes here, then goes here, and enters into the drain. Okay, this scenario takes place here in the channel region. This is called as diffusive region because it's like a diffusive motion, random motion, and it gives rise to resistance. Just a concept I wanted to give you. So now you have this linear regime in the whenever you have applied a small drain to source voltage. Now let's move on to another regime. Another regime. What will be the another regime? If you go on applying the drain to source voltage, you increase the drain to source voltage. Now how much? You increase the drain to source voltage and it becomes equivalent to the VGS minus threshold voltage. This term is something called as gate overdrive. This is very commonly used in CMOS technology. I will talk about it later on. If the drain voltage becomes of this order, how much is this value? We don't know right now. But if it becomes equal to this, the gate voltage minus the threshold voltage, what you see, the drain current, drain to source current versus the drain to source voltage, earlier it was like this, linear in this region. But then when the drain to source voltage becomes equivalent to VGS minus VTH, it begins to saturate. It does not exactly saturate like this. It does not become flat. It becomes like this, slightly increasing fashion. It does not become like this. It does not remain constant. There is a reason, something called a channel length modulation. We will study it in we will study later on something called a channel length modulation. What is CLM? We will study about it. But it almost saturates and starts to, I should say, look like this particular value. Now that is the fundamental thing about this. So you have these regions, you have this particular region, and then you have this particular region now of the current operation in the MOSFET. So that's why this region is called as ohmic region. Ohmic region. This is called as ohmic region. This is called as saturation region. And saturation region, you have one advantage that the current stays constant. Let's call it IDS1. So that's why it's used as a constant current source. Something called as constant current source. And because current is also varying with voltage, so you have a voltage controlled current source. Voltage controlled current source, something called as VCCS in electronics or electrical terminology, because the voltage is controlling this particular current now. In BJT, it's current control current source. Mostly the small base current you apply to in the BJT. Maybe you have not studied about BJT right now, but in the MOSFET, this is something called as voltage control current source. Okay. Now what happens? Now what is going to happen is that now you see this particular curve here. Let me take this. Now this is the fundamental curve of I should say output characteristics of a MOSFET. Let me remove this thing. This is something called as output characteristics of a MOSFET. Output characteristics. Output characteristics means drain to source voltage versus drain to source current versus drain to source voltage, but at particular gate particular gate to source voltage VGS. Okay, that means at particular gate voltage. This is at particular gate voltage VGS1. Okay, you have kept the gate voltage constant. Don't mix the things. You cannot change everything at simultaneously. You have to keep this constant, then start varying drain voltage. If you increase the gate voltage now to another different value, let's say VGS2, you will see what happens is that this will go like this, linear increase, then it will again saturate. Again, if you increase it to VGS3, this is for VGS2. This is let's make it like this. This is VGS2, and okay, this is VGS2. Then this is VGS3 is this one, linear increase. Then it goes like this. This is VGS3. Why does this happen again? Because you are increasing the gate to, I should say, you are increasing the gate voltage now. You are bringing in more and more electrons at that particular place, but it also has limit. Just like you know, everything is going to have a particular limit. You cannot go on increasing the gate voltage to a very high value. Otherwise, there will be oxide breakdown in between. Gate voltage you are increasing and you are getting these types of curves. But note that in this region it is staying linear. Just the slope is increasing. Slope increasing means conductance increases. That means the resistance decreases. Okay, that is making channel more and more conductive. This channel is becoming more and more conductive when you are increasing the gate voltage, because from the MOS capacitor you know that if you go on increasing the gate voltage, this will be more and more bended, and you have more and more electrons present here. Okay, so this is the MOS capacitor, MOS, and then there will be current flow in the channel when you will apply the source to drain voltage. That is what this particular curve is showing you. Okay, let me just add a page. Let me add up one more page. Add one page. All right. So, what next? Now, what we have, these were the, this is something called as, this was linear mode. This is something called as saturation mode, because the current saturation mode, saturation mode. And now what we are going to see is what happens in a saturation mode. I mean, why does it particularly saturate? Because let's take again the in saturation mode. Let me draw the transistor again. I like to make this transistor. This is the oxide. This is the gate. This is the body terminal. Let's say you have applied here the gate voltage, which is greater than threshold voltage, obviously, and you have applied the drain voltage equivalent to VGS minus threshold voltage, so that it is in saturation region. Okay, this is like this, and this is like this, and this is grounded. All right. Okay, so now what we have. Now, first of all, let's analyze this. You have a gate voltage which is greater than threshold voltage, and you know if you have greater than threshold voltage, you will be having electrons here because this is p-type. That means this channel is inverted. Let me draw a layer of electrons. Layer of electrons. Just applying gate voltage. Now you apply the drain to source voltage. Now what is going to happen? Electrons will start to flow in this direction. They will start to go here into enter this thing, and the current will flow in this direction. Drain to source current. That's fair enough. Now when the VDS approaches this value, something called as VGS minus V threshold, what happens is that the inversion charge at this particular region, Q inversion, becomes approximately zero. Now why does that happen? That happens because you are now, if you draw the, I should say, the band diagram of this particular MOSFET, it is similar to that of what you do in a PN junction. In a PN junction, when the PN junction is made in equilibrium, you have the band diagram like this. Constant Fermi level. This is conduction band, this is valence band, this is the Fermi level. Here, how you draw the band diagram? You consider these regions, and then you consider the middle region. You consider this region, you consider this region, and then you consider this region again. That means the pink regions are common, only the middle region is, I should say, the different one. Okay, there are three regions. So this one you have one region here, here, you have this region. That means for these two regions which are on the other side, this is at, let's say, you have not applied, let's say if VG is equivalent to 0, you have not applied any voltage, gate voltage yet, and VD is equivalent to 0. You have not applied drain to source voltage yet. I'm drawing the band diagram for that. You have both of these particular, I should say, you have this particular conduction band, you have this particular conduction band of the two ends of this device. Okay. Now in the middle, what you have in the middle, you have a something like a different type of, I should say, because you have induced electrons here in this region. Electrons are going to increase the electrostatic potential energy in this region. Okay, earlier, right now, we are considering the gate voltage to be zero. Let's assume the gate voltage to be zero. But what is going to happen is that let's say you have let's say you have a conduction band like this, and you have a region something like this here in between. It's like a barrier, just like in a PN junction, this barrier exists. Now, why is there a barrier? That is the question. Because you have N and P plus regions on this side. You have N region here, and this is P region, like a PN junction. Okay, so this barrier occurs because of this PN junction. This barrier happens because of this PN junction. I hope you got it. So now you have to deal with two barriers, and it's the same scenario. Let me just remove this thing. Oh no, I don't want to remove this. Let me just remove this. Okay, this is messed up. Hold. Let me remove this thing. So what happens basically when you consider N plus region and the P type of the drain, and N plus region of the source and the P type substrate, you have the same scenario here. I just want to show you that if you can visualize this particular thing. This is this particular region. Let's consider this region first. You have N plus here and you have a P region here. That means you will be having positive ion and excess electrons in this region. Positive ion, excess electrons. Same on this side. Positive ions, excess electrons. Because it's highly doped. So it's so highly doped there that the electron concentration is very huge, of the order of 10 to the power 18 or 10 to the power 20. It almost behaves like a metallic system, almost like a metal. So many electrons. It's something called as degenerate semiconductor. Okay, where the Fermi level is almost touching the conduction band. This is the Fermi level of it on these sides. And in the middle you have a p type, so Fermi level will be like this. So overall band diagram is something like this. This is the overall band diagram of it, where this is the n type, this is the p type, this is the n type. As simple as that, under no application of gate voltage and drain voltage. It's important to know. Now now the scenario is changed. Now because you have made these regions here, that means there is a depletion region here. Just like in a PN junction, there's a depletion region at this place. That means you have a positive ions on this side at depletion region, you have negative ions on this side. Similar happens in this MOSFET. You have positive ions here, but because the depletion region will be more penetrated towards the layer which is lightly doped. Okay, so more depletion region will be present on the P side. Depletion region spreads on the P side more. So this is the depletion region. So same happens on this side. It's a very complicated scenario on this side. You have two PN junctions, but I just want you to feel like the PN junctions. If you understood PN junction, you can understand everything. These are the depletion regions. And you know how much they spread. Let me remove this and this color. And you see how much they spread. This is the depletion width. This is the depletion width. And as the same you do for the PN diode, the depletion width can be found by under root twice epsilon by Q 1 over Na plus 1 over Nd V built in plus minus V applied. V applied here is drain voltage. This all same logic applies to here also. if you need to find the depletion width. It's not necessary most of the times to find this depletion width, but if you need. So this depletion region is present also here. It's present throughout. It does not discriminate. It's present throughout. So it occupies the part of the channel also. You see, now the part of the channel is occupied with these immobile ions, negatives and the positives from the depletion region. So this is the depletion region of this side. This is the depletion region of this side. And this is the channel. Now, further more complicated. Okay, depletion region always exists once the MOSFET is made. You don't need the voltage to make the depletion region, just like in PN junction. So let's talk about the band diagram now. This is the band diagram at zero gate voltage. So what happens when you just apply the gate voltage at VG equal to threshold voltage, but still VDS is equal to zero. You are not applying any drain voltage yet. Just gate voltage is equal to threshold voltage and drain voltage is zero still. When you apply the gate voltage, that means at this particular end, you're connecting a positive terminal, which is gate terminal greater than threshold voltage. If you are connecting this band, conduction band of this end to a positive terminal, positive voltage reduces the electrostatic potential energy of electrons. That means it will bring the band down. It is just like modulating this band. This band is like this. You apply the positive, it will bring it down. Just like you apply the positive on the in the MOS. If you apply the positive on the metal side, it brings this metal work function, metal Fermi level down, because metal does not have a concept of conduction band and Fermi level. It means it brings the conduction band down. It means that it lowers the electrostatic potential energy of electrons. So when you apply the positive voltage, let me show it here. When you apply the positive voltage, what happens? Let me just take it and duplicate it. This is when you apply the VGS is greater than threshold voltage. That means this is positive. You apply the positive voltage. This band goes down because of application of positive voltage. Because positive voltage lowers electrostatic potential energy. So this band comes here like this. See the blue line. Now this is the band when you apply the, I should say, positive voltage. Okay. Now what happens further? You go on increasing the positive voltage. You go on increasing the positive voltage. This band further goes down. This is like a hill. You are reducing the hill. And you know what happens when you reduce this particular hill. Now you have more chance of electrons on this side and this side to go into the channel. Just like you have the electron distribution here, same old distribution N of E, which is the product of density of states times the Fermi function. Just like this distribution. This is increasing then exponentially decaying. These two distributions are present everywhere. This distribution is present everywhere in the devices, in the conduction band for the electrons and in the valence band for the holes. This is for the holes. This is for the holes. Okay, this is the distribution of electrons as a function of energy. Now you have reduced this barrier down, you have made this barrier down, brought this barrier down. Now what? Now you just need small voltage at these terminals. If you, let's say, because you have electrons here, you apply negative voltage here, apply positive voltage here, electrons will go, and because the barrier is lowered, electrons will go in this direction now. As simple as that. So now electrons can flow. Earlier the barrier was high, so only maybe these few electrons were able to cross the barrier. to cross this level. But now you have brought this level to this position. Now more electrons will enter. As simple as that. Okay. So electrons will now move from source towards the drain end because you have applied negative on the source. And now that is the conduction. The conduction will happen. There will be huge conduction in the channel. But this flow will happen only if VDS is not equivalent to 0. Now, that means the third case. When VGS is equivalent to threshold voltage, let me write it as when VG is greater than threshold voltage and VDS is non-zero but small value, millivolts. This is the third scenario. Let me keep it same. What happens because of it? Because now you have lowered the barrier. The barrier is lowered. The barrier is lowered. Okay. So you have the electrons going from this region to this region because you have applied positive here, negative here. This is source. This is drain. Gate already you had applied the VG greater than threshold voltage. That brought this band down. That is already shown. So now electrons can freely move. But the important point, the Fermi level also splits. We are not talking about Fermi level. At equilibrium, the Fermi level was flat. This Fermi level was flat. Now here, you don't have a flat Fermi level. What you have here, because you are applying negative on the source end, the Fermi level goes up here. The Fermi level goes on this end. It goes down because you are applying positive on this side. And one mistake I did is this won't be like this because you are applying positive on the drain end. That is the main point of this. I'll redraw this band diagram for this case. For this case, when gate voltage is greater than threshold and drain voltage is non-zero but few millivolts. Let's redraw the band diagram. Let's redraw the band diagram. Okay, so it'll be like this on the source end. Then it'll be something like this because the barrier has gone down. Earlier the barrier was like this, but now it is this barrier. You have applied a negative on this side, source side. You have applied, let's say this was drain side earlier. Now you have applied positive. Positive will bring the conduction band down. Positive means electrostatic potential energy of electrons reduces. So it will bring it down here. Okay. इसका मतलब यह है कि जो सोर्स एंड भी है वो भी उसी अकॉर्डिंग ऊपर जाएगा because you are applying negative here. Negative will increase the electrostatic potential energy of electrons on the source side. So this will go higher. यहाँ पे जो बेंडिंग था वो ऐसे जाएगा या जो हिल बन रहा था this hill it will go like this, and because you have applied positive on drain side this end will go down. So this is the drain side now. This is the drain side, positive applied. Now you have to connect this region to this region. It looks something like this. This is the overall bending. Now you see the huge bending. You see the huge bending now. And how we got to it? Just from simple electrostatics, positive and negative. And let's draw the valence band. The valence band will also follow the same thing. This is the valence band. This is the valence band. This is conduction band, valence band. Conduction band, valence band. Now let's talk of Fermi level. Yeah, this region Fermi level will be here, down. This region Fermi level will be here because this is N plus type. This is also N plus region. Okay. And this region is the region of interest. This is the P region, which you have inverted because of application of gate voltage greater than threshold voltage. This region, earlier it was P type, but now you have converted into N type. how will the Fermi level look like? It will look like something like this. It will go like this. It will go something like this. Basically, it enters into the, let me just make it like this. It remains flat up to this particular region. Fermi level has to be flat. Then it enters into this region, and there is a this particular thing here, the gradient of the Fermi level, in which indicates the drift of the charge carriers. So this region was p-type and n-type. Okay, let's draw this particular Fermi level here. So this is the Fermi level of this particular structure. So now you see that what has happened basically is that you have, in a way, and this is particularly electron Fermi level, just to mention it. So what has happened now? Now the main thing, just think about this particular band. You have created such a band bending that if some electrons are present here, they will just rush towards this end because of the drift, because there's huge band bending at this place. And why is there a huge band bending? Think about it in terms of p-n junction. This is n plus, this is p. You have applied positive to the n plus, and you are applying positive to the n plus and negative to the p-type. Why p-type is negative? Is because it's connected to the lower end of the substrate. That means, in short, the N plus region is connected to the higher potential as compared to the P-type substrate. That's the concept. What does it mean? It means this particular PN junction, there are the two PN junctions I showed earlier. Where is that figure? This particular PN junction. You have N plus, region here. Let me redraw it. N plus P. This is one PN junction. This is another PN junction. It is all connected to the body. Okay. So now what you are doing here, you're connecting negative here. You're connecting positive here. In this region, positive is connected to the N plus side. And this is all grounded. Let's connect this to the ground. And in this region, N plus is connected to the negative end. What is going to happen? This is all grounded. Let's consider. And this region particularly, you have this oxide, you have the metal, and this is gate voltage greater than threshold voltage. Okay. So because of the incoming electrons are going to go like this. They are going to enter the channel. They are going to go through this. Just like all the electrons which are here, they are going to enter here. They are going to enter here. And once they reach here, they just drop down because of drift velocity. This slope, dEc by dx, is the electric field. And once the electron reaches this point, it just goes down the slope and gives rise to current, huge current. Okay. So now what else? What now? What happens if we further go on increasing the drain to source voltage and it becomes equal to the VGS minus VTH? We want to analyze that scenario in terms of the charges also. And we have not talked about that yet. So what happens if we have this region N plus, this is oxide and this is metal, this is P-type. Okay, let's apply the voltage, which is VDS is greater than VGS minus VTH, greater or equal to, let's say, and this is connected to negative, and this is VG greater than V threshold. You know that there was inversion charge present here, a uniform layer of inversion charge present here. But what happens when the gate voltage crosses or at least reaches this particular value? is that this charge, let's say this charge was like this earlier. It was like a uniform charge of this. Let me show it more thick. It starts to make a region like, oh shoot, it starts to make a region like this at this particular place. Now the charge region looks something like this. That means as it approaches the drain point, the charge almost becomes negligible. This is something called as pinch off. Pinch off means it's like a pinch of a pinch of something. It's like a little bit of charge present there or negligible. And now it so happens that if you go on increasing the drain to source voltage beyond this value, the channel or the charge further reduces and it shifts. It becomes like this. Go on increasing the drain voltage further, it increases like this. I should say it shifts like this. It shifts like this. It shifts like this. So it means that you are changing the channel basically because of the drain voltage, which should not have happened because only the gate voltage would have been able to control the channel. But now you are controlling the channel with drain voltage. Okay, earlier the channel was like this. Now the channel is only up to this region. You have shifted the channel. Let's say this was the channel earlier, channel length earlier, LCH. Now this is the channel length, the blue one, LCH dash. That means overall channel length is now, that means you have reduced the channel length from LCH to LCH dash by applying VDS greater than VGS minus V threshold. Okay, so that is, you have modulated the channel. And this is something called as channel length modulation. You have modulated the length of the channel with the help of the drain voltage. And why does this happen? Again, because these regions, you have these depletion region present here. And you know that the electric field will be in this depletion region will be in this direction. That means in this direction. This is the direction of electric field in the depletion region, the built-in field. Let me draw it. This is when you have applied drain voltage. This is the conduction band. Let me just draw the conduction band. This is source end, negative voltage, drain end, positive voltage. And this is the conduction band. You have a whole lot of depletion charges here. Okay, these are so huge that you know that there's a built-in electric field present here. All right. So what that built-in field creates is that any electron which is present here will be drawn into that particular field because electron force on the electron is opposite to that of the electric field. So if the field is in this direction, the force on the electron is in this direction. So that is what is basically also shown by the bending. So electron will go in this direction. It will rush into this particular direction. Okay, that is point number one. And point number two is this particular depletion charge, it is also present at these regions. Let me draw it like this. And what happens if you apply the gate when you apply the gate voltage greater than the threshold voltage? That means you have positive charge on the gate side You have negative charge on the electrons in the channel. Okay. But now if you have, let's say, negative, you have also negative ions here just beneath the gate. Okay. That negative ions can basically shield the electric field from the gate. This electric field. There is also electric field in this direction. Okay. From the positive to the negative end. And if you consider the depletion region, this depletion region, these negative ions are basically shielding the electric field from the gate. That means you might have to apply more of the gate voltage in order to induce the channel. That is point number two. And one thing to note here is that because the channel has now moved away from the drain point, there is a, I should say, inside the channel, if you have this is channel LCH. Let's say this is x equals to 0 and this is x equals to L. This is this region. If you draw the potential profile, you will get a potential something like maybe this, where this at this point the potential is VDS, and you have connected 0 at the source terminal. This is the source terminal. This is the potential profile inside this particular channel. And let's say if you have to draw the charge profile inside the channel, it will look something like this, where this is x equals to 0, this is x equals to L, and this is the source end, this is the drain end. And this is Q inverted charge as a function of x. This is the x direction. Considering x to be in this direction, let's say this is y direction. Okay. Now, what else? I think we have spent a lot of time, and it's a very deep topic. Let me just cover some more things. Maybe I have to cover. This thing we have covered. Okay. This thing we have covered. What else is there? Let me talk about this. Yes. Okay. So this is the overall scenario in this MOSFET. Actually, there are more things to talk about, but maybe we can talk about it in the next session because we have to solve the questions. But briefly, we will talk about what how things manifest in it and how you obtain the current voltage characteristics of this particular device. So let me just check this thing. Okay, where is this? Yeah. So hope this does not fit up. So now this was the basic, I should say, the overview of it. It's in fact deeper than this, and the main important thing is that these particular devices or these particular diodes are always reverse biased with respect to each other, or they are reverse biased so that current should not flow in this particular direction. Okay, we bias it in that particular fashion. Now, and they are the crucial elements of the, I should say, the MOSFETs. But I'll talk about those particular PN junctions in the next class, maybe next session, and how these depletion charges play a crucial role in modifying. But right now, maybe we'll talk about current more, IDS. Okay, let's talk about current. So you know that the threshold voltage you have studied from the MOSFET, MOS capacitor. You knew about the threshold equation, which is the flat band voltage minus the uh, inversion charge plus the I should say the flat band voltage. Let's remove this. The threshold voltage is basically the flat band voltage plus I should say some fixed charge inside the oxide divided by oxide capacitance plus the inversion charge divided by the oxide capacitance and plus twice that of the Fermi potential. That is the overall threshold voltage of a particular device. And if you want to know the gate voltage basically can be given by the flat band voltage plus minus the depletion charge plus the inversion charge divided by oxide capacitance plus twice the Fermi potential. Fermi potential is basically uh, the EI minus EF, the difference between the intrinsic and the Fermi level in the bulk. That is the Fermi potential. Okay, even not in the bulk, even in the entire semiconductor, it's applicable. That is the concept of Fermi potential. And you exactly identify this particular thing, that the uh, flat band voltage minus the QD by Cox plus twice phi f is actually the flat band voltage is actually the threshold voltage. So you can write the gate voltage to be equivalent to the threshold voltage minus the inversion charge divided by the Cox. That is the overall gate voltage you apply. And what does this equation mean? This equation basically means that whatever the gate voltage you apply, that is going to drop in the device. That is going to drop in what things? First, to make the bands flat. Second, to make the depletion charges. Third, to create inversion. That is the overall drop in the uh, gate voltage you are going to apply. It's just like KVL. You have KVL, you have a voltage source, and you have certain resistors, and you will have voltage drop across resistance R1, R2, R3. Okay, so first drop will be because of flat. You have to make the bands flat, which depends upon the work function of metal and work function of semiconductor, its difference, and it depends upon the if there is any fixed charge inside the oxide. You have to make all the bands flat. And second voltage drop is because you have to go into the depletion region first to create immobile ions in the depletion region. Then you enter into the inversion region where you have immobile ions as well as the electron density near the semiconductor and oxide interface. Those are the voltages which get dropped, which create these particular scenario. Now you know that the overall current can be written as, because the current flows because of inversion charge. So current is charge per unit time. Let's call it T. And you can, from this equation, you get Q inversion to be equivalent to minus Cox Vg minus V threshold. You can use this Q inversion here. You can write it as minus Cox Vg minus V threshold divided by time. What is this time? You can write basically velocity is distance per unit time. Distance means channel length per unit time. So you can write time is channel length per unit per velocity. This is drift velocity. So you can write L to be mu times electric field, because drift velocity is mu times electric field. Okay, so let us add the page. So now you can write T to be equivalent to L mu E. Electric field is voltage per unit length. So you can write L over mu voltage per unit length, and you can write it as L square divided by mu. Voltage is basically the drain to source voltage you apply. So this is the time T. So you can replace this time here and you get minus Cox Vg minus Vt L square over mu Vds, and you can write it as minus mu Cox Cox minus mu Cox Vg minus Vt into Vds divided by L square. All right. So this is IDS basically. But we are talking about current, I should say the current density mostly. That means current per unit area. So you have to multiply it with area. So you get current is equivalent to minus mu Cox L square Vg minus Vt Vds into area is width into length. Length and length will go. You have minus mu Cox divided by L into W VGS Vg minus Vt into Vds. This is the drain current flowing depending upon the drain voltage and the gate voltage. overall. Now there are certain regimes. This is in the linear regime fashion. In the saturation regime, you may have a VDS square dependency accordingly. In the saturation regime, where the equation gets modified to something like mu n Cox W by L VGS minus VTH square minus VDS square divided by 2 overall equation. So accordingly, you can modify these particular equations. Okay. And now one important concept I want to mention here is something called as gradual channel approximation. Gradual channel means you neglect the change in the, I should say, electric field in the channel, and you consider most of the electric field is in this direction. Let's say if this is y direction, this is x direction, you consider EY to be much, much greater than EX. But this is only applicable if you have a long channel. If this channel length is very long. And what does this happen? I mean, what it helps us is to make it easier to solve the Poisson equation. You know, the Poisson equation is basically del dot E is equivalent to the charge per divided by epsilon. Okay. So you can write it as basically dou by dou x of Ex plus dou by dou y of dou y plus dou by dou z of dou z equals to rho by epsilon. But if you don't want to, let's say, consider maybe these particular other gradients, you can neglect those variations. And you just have to solve it in a one-dimensional case, which is maybe you can consider dou Ey by dou y equals to rho divided by epsilon. That will solve your problem. But this is only applicable if channel is long. If the channel becomes short, that means this dx and dx becomes, if dx becomes small, that means dou by dou x becomes huge. The change in the this particular thing becomes huge. Okay, so then you cannot use this particular approximation, which is something called as gradual channel approximation. So that's why in the short channel devices, in the short channel devices, the GCA fails, and you cannot simplify the Poisson equation and the other things. You need to fully solve the equations by considering the variations in dy, dz, and dx, obviously. So that is what it happens. It helps us. Now, other thing I wanted to discuss, maybe let me check. Just okay, this is done. This is done also. All right. Okay, so that's it. I think we should jump to the questions. Maybe we can discuss about it in the other session. We just have half an hour left. Let me just open this particular section. This is it. Okay. All right. So I had planned to discuss these things, but we have gone past through the time. So let's quickly discuss about the questions. First question, why did we take the area as WL? Shouldn't it be the channel thickness into the why do we take the area? Should it be the channel thickness times the width, since area needs to be perpendicular to the current flow? Okay, so you are saying why did we take, let me draw it, like 3D source, drain, no, this is not the oxide. This is the oxide, and this is the gate over it, and this is length, and this is width. Now say, I hope you got the answer from this 3D visualization. Why the area is W into L. So you have to imagine it in 3D. Current is not flowing in a 1D fashion like in this region here. It is throughout flowing in the three-dimensional, I should say, like this fashion. So the area it will, I should say, area will be the overall channel length, this channel length, into the width, this particular overall spread of the entire channel in a 3D. It's a 3D. It's a slab. It's a slab. I should say the current moving in a slab type fashion. It's like this. It's like this. So the electrons are moving throughout. So if you consider a plane, this plane, you can if you compute the flux of electrons, that is the number of electrons moving per unit area. What will be that? That will be number of electrons divided by what area? This particular thing, the width of it into the overall. If you consider now, if you consider this particular thickness also, that will be the length. This is the length, and this is the width. That will be W into L. Simply the flux of these electrons. I don't know why it's confusing to you. Since area needs to be perpendicular to current flow, it is perpendicular. It is perpendicular. You see this red plane, which I have highlighted in green. Electrons are moving perpendicular to that plane. What other length? That will be top area, right? No, that is the area throughout this particular channel. That's what you're not imagining. This is the channel throughout this structure. The channel is not just present at the front end. It's present throughout, near the surface. It's present throughout. If you see this channel here, it is present below it throughout. It's not only present on the front side, it's present throughout, just beneath the oxide, throughout. Lekin. And if the electrons are moving in this direction, and if you select a plane, those electrons will be moving perpendicular to those planes. Okay, and you can compute the overall area of that will be the width into the length of this particular thing. Just like if you have a plane, current will always be moving perpendicular. That's how you compute the flux, the number of lines passing through this per unit area. That is the overall flux. Even if you just consider if the water is flowing, just bring a frame in front of it, rectangular frame, which is having this side as, let's say, W, this side as, maybe let's say this side is L, this side is W. Then you can know that the number of water lines passing per unit area is the flux, water flux, where this is W into L, the width into length of that particular frame. I hope you got the answer. Just little bit more visualization because it's a 3D. That's what I initially talked to you. It's all happening in a overall layer below the oxide throughout. That's what makes it more difficult to imagine. It's not just happening at the front view. It's happening throughout. Okay, so let's jump on to the questions immediately. For an ideal p-type depletion MOSFET, choose the correct statement. It's a depletion type MOSFET. That means already inversion will be present. Inversion channel will be present. If the already channel will be present, that means there will be a whole channel present even at zero applied bias. That means you have to apply the bias to make it off. That's what we discussed earlier. It's a normally on transistor. Depletion mode transistor is a normally on transistor. You have to apply the bias to make it off. That's the overall concept of this question. First slide of my session about enhancement and depletion mode transistor. Let me remove this. Now
Got
consider
it,
an
sir.
N-channel MOSFET. N-channel means NMOS. That means P substrate. That means electrons are in the channel. First thing. All right. So all the parameters are given. This is something called as transconductance parameter. Transconductance parameter. Transconductance parameter. And it is the same which we wrote. IDS equals to mu n C ox W by L VGS minus VT into VDS. This particular thing is called as transconductance. Okay, this is called as K, transconductance. And it has the units of milliamps per volt square. All right. And what is basically conductance is conductance you can write G, that is 1 over resistance. That means this particular term is basically 1 over resistance. That should be, because this is voltage, this is current. So I is equivalent to V divided by R. V equals to IR. It should boil down to Ohm's law. Yeah, at least in this case. Okay. In the linear case, not in the saturation case. In the saturation case, it should be, it's not, V equals to IR is not followed in the saturation case. That means Ohm's law is no longer valid in the saturation case because V is not linearly varying with the, I is not linearly varying with the V. So that is the overall thing about. So W by L has been given. Threshold voltage is zero point 0.4. That means if you apply gate voltage greater than threshold voltage, that means greater than 0.4, you will have inversion. So you have to compute the drain current for VGS equal to this and VDS equals to this. Whenever you are given such questions, first of all, think about in which mode is this transistor, in which region is this transistor, whether it is in linear region, whether it is in subthreshold region, or whether it is in saturation region. Just how you do it by computing the VGS minus threshold voltage. How much is it? VGS is 0.9 minus 0.4, that is 0.5. So you get the VGS minus VT as 0.5. Now you have to compare this value with drain voltage, drain to source voltage. Drain to source voltage has been given as 1 volt. So you see that VDS is greater than VGS minus VT. If it is the case, that means it's in saturation region. It is this region which we showed. If this is IDS, this is VDS, it is linear up to this point, and then it saturates. This is VGS minus VT. And this is, we are talking about now this region because you have got the VDS to be much greater than VGS minus VT. So this device is in saturation region. So if it is in saturation region, you have to use the equation which looks something like IDS equals to mu n C ox W by L VGS minus VT square. This is the overall, this is the equation in the saturation region. And this relation, this particular thing has been given transconductance. So this is kappa, let's call it K kappa. And this is VGS minus VT square. Everything has been given. You just have to compute the current. And I think there's a 2 here basically. I missed that 2 because this equation is basically VGS minus VTH minus VDS square divided by 2. Yeah, so there's a 2 here. So this is basically kappa by 2. And when you compute it, what is kappa? Kappa is 1, but milliamps. So 1 milliamp per volt square. Okay. And this particular thing is 0.5 square divided by 2. You solve it, you get IDS value to be approximately 125 milliamps. So 125 milliamps is the answer of this question. Okay, yes, this is done. Did we do it correctly? Hmm. Okay, so let's move on to the other question. Question number 3. So now consider an ideal long channel N MOSFET, again N MOSFET. That means NMOS, same MOSFET. You have mu and Cox given as this value, W by L given, threshold voltage given. You have to compute the drain current again for this gate to source voltage and for this drain to source voltage. Okay, so now what you do, again check the region. In which region is this transistor? Whether it is in linear, saturation region or subthreshold region. For that you compute VGS minus V threshold. How much is VGS? 0.8 minus V threshold 0.4. You get 0.4. VDS has been given as 0.1 volt. That means VDS is less than VGS minus VT. That means it's in linear region. It is this region, because it's less than. Now for this region, overall current IDS equation is mu n Cox W by L VGS minus VT square minus VDS divided by 2 square. Yep, yes, this is the equation. So now again overall everything has been given. This is given, W by L is given, this thing has been given, and VDS is also given. You get
Okay, sir.
0.18 into 10 to the power minus 3 because it's in mu and Cox is in milliamps. W by L is 8. VGS minus VT you computed, that is 0.4 square. VDS is zero point 0.1, that means 0.1 square. You compute this thing, you get the drain to source current as 0.050 milliamps approximately. Which option is it? 0.050. Okay, this is 504. So this is the correct answer of this question. The important thing about these questions is to just check the region. In which region is it? Then apply the current equation accordingly. Okay. The only problem arises when at this particular point, because these equations are not applicable at this particular point. They blow up at these particular points, and you have to solve a different type of problem for that, which we may take a different session to basically go into that, why these equations are not applicable at the particular regions. So that we will maybe deal in next session, but I had planned to cover it in this session, but time is running fast. Okay, let's move to the fourth question. So the fourth problem says the subthresholds, about the subthreshold swing. The subthreshold swing is defined as, okay, what is subthreshold swing? Just briefly, let's briefly discuss about it. The subthreshold swing is basically the change in the drain voltage with respect to the, oh God, the subthreshold, this particular subthreshold swing is basically the change in the drain to source voltage with respect to the with respect to VDS. Okay, sorry, with respect to gate voltage VGS. So this is called a subthreshold slope. And if you draw this axis in log scale, and this is VGS in volt, you get the region something like this. Why? Because this is almost like drain current increases because of gate to source voltage. Note this is gate to source here, not the drain to source voltage. So it is the same thing what happens in diode. It's like this exponential increase. So when you draw it in log scale, it looks something like this. Okay, the conduction takes place only when the gate voltage reaches the threshold voltage and beyond, just like diode. In diode, if you cross the cut-in voltage, you get the conduction. In MOSFET, when the gate voltage becomes threshold voltage, you have inversion at this point, channel inverts, current increases exponentially. And if you draw this on a semi-log plot like this, you get a this type of curve on a log scale. You have to basically write I equals to I naught e to the power qv by kt minus 1 diode equation in a log plot. Okay, you write it as I divided by I naught equals to e to the power qv by kt minus 1. You can write it as, let's ignore 1 for a moment by considering voltage to be much greater. Okay, if voltage is greater, you can ignore 1. You can write it as ln of I by I naught equals to e to the power qv by kt. Oh, sorry, e goes qv by kt. You write v equals to kt by q ln of I divided by I naught. So you got this. You can now plot, let's say, ln of I by I naught versus v by kt. Okay, if you plot ln of I divided by I naught equals to uh, q by kt times v, and if you plot ln of I naught versus v, that is this particular plot. Just the concept here is that this I is basically drain to source current, and this v is vgs, and this is the slope kt by q. Okay, and this slope, this is called as subthreshold slope. Subthreshold slope. Okay, why subthreshold? Because it is the condition when threshold you have slightly less voltage at the gate terminal than the threshold voltage. Okay, that is what basically the concept of subthreshold slope is basically. But this is the overall concept. And when you compute this particular slope, you know that if you have straight line y equals to mx plus c, m is the slope. Here this m is kt by q. Or it should rather be q or kt. It should be inverse of it. Okay, so that is the particular slope of this particular. That is the particular slope of this line, and that particular slope is called a subthreshold slope. It tells us that what is the change in the drain voltage with respect to the gate voltage, and this is very important parameter in designing the MOSFET. And when you compute it, particularly, I don't know what is the question here. Subthreshold swing is defined as the increase in the gate voltage when necessary to increase the drain current by the factor of 2, the increase in the source voltage necessary to increase the drain current by the factor of 2, increase in the drain voltage necessary to increase the drain current by a factor of 2, the increase in the gate voltage necessary to increase the drain current by the factor of 10. This is I think this should be the answer of this question. Why? It is basically, we have talked about subthreshold slope. You have subthreshold, you have two things. Don't confuse the two things. You have subthreshold slope and you have something called as subthreshold swing. These are two things inversely related to each other. Basically, you have subthreshold slope inversely proportional to subthreshold swing. Okay, so this particular thing is here swing, subthreshold swing. We talked about. Don't confuse. If you know the subthreshold slope, you can compute the subthreshold swing. They are inversely related. And this is the subthreshold swing here we talked about. It swing means it tells you how much current is swinging with respect to the gate voltage by changing the gate to source voltage. So basically, this is the particular thing which comes from the basically comes from this diode equation. It tells you about that it is the increase in the gate voltage necessary to bring about a decade change in current. Decade means 10 order of magnitude change in current. This is in log scale. So if it is 10 to the power minus 6, 10 to the power minus 5, 10 to the power minus 4, 10 to the power minus 3. So it is the current, it is the gate voltage to bring this particular change. The gate voltage needed to bring this particular change, an order of magnitude change. You see that from this to this, a decade value has changed. It has increased by an order of 10. So this particular voltage, delta V, this is delta I. So subthreshold swing is the increase in gate voltage from V to V plus delta V necessary to increase the drain current from, let's say, I to I plus delta I by 10, by a factor of 10. And this factor of 10 comes from solving these particular equations basically. If you put 10 I divided by I naught equals to e to the power qv divided by kt, you will get the definition of subthreshold swing. That is the overall fundamental concept of it. And this is the exact question I was talking about. What is the minimum subthreshold swing minimum of a classical MOSFET? You see that the units is millivolts per decade. Decade means order change of the order of 10 in the semi-log scale. That is what decade means here. And you have to compute this in what is this thing? Oh God. And you have to compute this particular thing in at T equals to 300 Kelvin. Okay. So that is the thing I was talking about. You will get subthreshold swing to be equivalent to KT by Q ln of 10. Ln of 10 means, why does this come from? Ln of I by I naught. So if this KT by Q remains same, and this becomes 10 times I by I naught. 10 times, or I should say I naught by I naught, and you can write it as KT by Q ln of 10, and this becomes KT by Q. This is 2.303. If you solve this, you get subthreshold swing. And when you compute this, you get 60 millivolts per decade. And this is basically set by the Boltzmann distribution, Boltzmann factor. It means that this is the minimum change in the current which you will get by changing the gate to source voltage. You cannot get a value below than this. You cannot get a faster
So
change than
what
this.
is
And
decade
this is
to
basically
length
set by
of
what? This is set by this KT by Q. And that's why at T equals to 300 has been given. If you reduce the temperature, you will get a lower subthreshold swing. But what is now determining this, how fast you can change the, I should say, drain to source voltage with respect to the gate voltage? What determines that is temperature. That means nature, the Boltzmann factor, the Boltzmann temperature, the Boltzmann distribution. If you play with those distributions, you're going to reduce the subthreshold swing. And that is why I
Thank
showed
you,
here
sir.
this equation. The Q by KT basically gives you the subthreshold slope. Subthreshold slope. And you see these two are inversely proportional to each other. So subthreshold slope is inversely proportional to subthreshold swing. Swing tells you how much current varies with gate voltage. The gate voltage point is important here. That is the important concept of subthreshold swing. So the overall answer, the question is 60 millivolts per decade. You cannot go below this value. It's the minimum value set by the Boltzmann distribution, Boltzmann factor basically, because this is temperature dependent thing. That's why the temperature has been mentioned here.
sir, what
So
is
it is
millivolt per
important in
decade?
the devices right now, because if you want to make a device faster and to run the faster and faster, you have to play with the subthreshold swing of that device. Okay, it tells you about
Boltzmann
how
constant,
faster
sir,
this
due to
how faster these
classical
charges in
MOSFET.
the inversion layer can respond to the gate voltage. Okay, so the faster they will respond, the better it is for the device. Slower it will respond, slower will be the device. So people always try to improve this subthreshold swing. But at room temperature, where our devices are operating at, it is set by the temperature. If you lower the temperature, you get a better subthreshold swing. Why is that the case? That is a different scenario. That is, we have to go deeper into learning the physics of it. So now moving on to the question number 5 and 6. What are
Hello,
those
sir.
questions telling us?
Hello.
ID versus VGS characteristics determined for an N-channel MOSFET are given. The This is ID versus VGS. Okay, this is something called as transfer characteristics. Yeah, K. What is your name? Hemant, you have a question.
Hello,
You're
sir.
not audible.
Am
No,
I
no, no,
audible?
you're not audible. I'm not able to hear you, but I'm able to see your message. Can you just quickly tell me the question because we have overshooted the time and I have to finish it. No, you are not audible at all. If anybody else is able to hear Hemant, they can respond, but I am not able to hear you.
Hello, am I audible to anyone?
Uh, I'm not able to hear you.
Yes, you can say.
Oh, you can hear. Is that the problem with
Hello.
my speaker? Yeah,
Hello.
yeah, yeah. Speak, speak, speak. Now I'm able to hear it.
Uh, Sir, am I audible now?
Yeah, yeah. Now you're audible. It was some
Just I
issue with
had
the
a
mic.
normal question like what is millivolt per decade means?
Yeah, yeah,
It's in millivolt convention, but millivolt
yeah.
per decade means.
Oh God. Yes. Millivolts, it's just a convention. Whenever you have a, let's say a decade, it's mostly used in semi-log plots. Semi-log plots means whenever you have one of the axes, this is y-axis, this is x-axis. Whenever you have one of the axes in log scale. So whenever you have whenever you have huge changes in the values, you usually plot it in log scale, just like we have plotted the current values here. IDS
Yes.
versus VGS. So this is in millivolts, and decade means this has been taken in log scale. So this is, let's say, 10 to the power minus 6, 10 to the power minus 7. Oh, sorry, 10 to the power, let's say this is 10 to the power minus 8, 10 to the power minus 9, 10 to the power minus 10, 10 to the power minus 11. Decade means a change of this single order change, 10 order change. ठीक है? If a current is going from this value to this value, it is changing by a factor of 10. That means it's changing by a factor of decade. That is how the units come from millivolts per decade. Per decade means per 10.
Okay, sir. If it is
Yes,
Okay.
in
suitable for calculation.
Yes, it is suitable for calculation as well as to show the large changes, because if you want to show a change of 10 on a linear plot, it will be a huge change and you have to draw it on a very large scale basically. That's why whenever you have such huge changes, you draw it on a log scale. Okay,
if
you
it is an
mostly sim.
exponential case, it's not the decade.
Hmm. Yeah, if it is just the exponential, then you don't have to consider the decade. You have converted this into a simple
LN scale.
exponential plot to a lawn plot. If it is exponential, just like IDS versus VGS, you have changed like this. This is the threshold voltage. Then this is in some milliamps and this is in millivolts. Okay,
Okay, sir. Okay,
that
okay.
is the
I got
case. And that is why these the particular thing, if you have noted, this unit is in millivolt per decade, but here it will be the linear units, not the decade or something. It will be amps or the whatever is on the y-axis. Okay, that's why the units. That's why you see
Okay,
here it has been written micro amps and this has been written as volts, because this is just a linear plot.
okay,
All
sir.
right, so what is the question? IDVGS, the transfer characteristics. What is transfer characteristics? This is the transfer characteristics of a MOSFET, let's say in general MOSFET. Transfer word is used at the time whenever two different quantities at different ends are compared. What do I mean by that? Here you are plotting drain current, but you are varying gate voltage. These are two different terminals. Whenever you are varying voltage at other terminal and measuring the current between two different terminals. At that time, you use the word transfer. Okay, just like you have N plus, and you have oxide and gate. You are varying this, but you are getting change here in the IDS between these two terminals. Okay, this is like an indirect change in the IDS because of VGS, because of VGS. Usually what should happen, that IDS should change because of application of voltage at these two terminals. But here in the transfer characteristics, you are measuring the change in IDS because of the VGS. That's why the word transfer is used that time. Okay, that is why the word transconductance is used. Wherever you see the word transconductor or transfer characteristics, trans impedance, assume all the time or think about that this is a change brought about by some other terminal between the two other terminals. Okay, unlike output characteristics of a MOSFET, output characteristic is simply output current versus output voltage, or output current IDS versus VDS. But this is output current and this is input voltage. So that's why it's transfer. Okay. And in fact, the name of the transistor basically itself comes from transistor. Okay, there's a transistor in a transistor itself because it is just like it's like a transfer of electrons from some high resistance part to the low resistance part. It's a resistor and it's a tran. It's the transfer of current and or the electrons between high resistive and low resistive states and paths. That is the basically the fundamental thing of why it's called as transistor. Let's leave that. So assuming the drain voltage to be of this value and oxide capacitance, the mobility of the carriers in the inversion layer you have to find. Okay. So what we are given here, the first of all we need to think about what we are given here. We need to find the mobility. Where do we see the mobility? In the drain to source equation, you see that there is mu n C ox W by L VGS minus VT square minus VDS square divided by 2. Here you find the mobility. Here is the mobility. Now you just have to compute it by using the already given data. Let's say, for example, you consider this particular point. At this particular point, point 1, at point 1, you have VGS to be equal to 1 volt and IDS is given as 25 volts. Okay, using these values, you can basically compute this particular thing because other things have been given. What other things? VDS has been given and width and length have been given. Cox has been given. When you compute it, you get one equation because threshold voltage is not known. This is unknown, I guess, threshold voltage. So there are how many unknowns? There are two unknowns. There is mobility unknown and there is threshold voltage as unknown. So let's solve this. Let's particularly solve this. So let's solve at point 1. You get let's say how much is the current? 25 microamps. This is in microamps. So you have 25 into 10 to the power minus 6 is equivalent to mu n. Cox is 8 into 10 to the power minus 8 farad per centimeter square. You have to take care of the units. 8 into 10 to the power minus 8 farad per centimeter square. Let's keep it in centimeter for now. And this is how much is VGS minus VT? This is 1.5 minus V threshold square minus 0.1 square and divided by 2. Now you see that this is unknown, this is unknown. When you solve this equation, you get an equation in terms of mu n and Vt. You get an equation like this: 250 divided by mu n is equivalent to 0.2 minus 0.2 times Vt. Maybe this is 7. This is equation 1. Again, you have to solve at this particular point using the same fundamentals. Okay. So when you reach another equation, because you have two variables, you need two equations to solve it. When you get the other equation using these values, you get the other equation as for this particular thing is equivalent to 0.49 minus 0.2 times Vt. Now you have a simple, you just solve these two equations, subtract or add, whatever you do, you are going to get the mobility value. Maybe that is approximately 500 centimeters square per volt second. 500 centimeters square per volt second. That is the overall mobility value. Just by solving using this particular equation. Now, what
Okay,
is the
sir.
next question? What is the next question? Let me draw this fastly. Let me show it. The mobility of carriers in inversion region. Is this a same question? Why is it repeated? Oh, it's the same question. Sorry. So it's a 500. Okay. Question number 7. The threshold voltage of MOSFET is. You have to compute the threshold voltage. This is pretty much easy. Now you have computed the. I guess this is for the same part, right? Yeah, this is for the same part. You have computed the mobility, just put it in here, you get the threshold voltage. As simple as that. And the threshold voltage you will be getting is 0.875 volts from the previous equations. Okay, just because you now know the mobility, you can put the value of mobility in either equation A or equation B. Either here or here, you get a threshold voltage. That's as simple as that. And I guess the threshold will be around 0.875. That is for part 7. And part 8, let me just see. Given below are the two statements regarding drain current in conventional PMOS and NMOS device. Okay, what is PMOS and NMOS? NMOS is N channel. I have talked about. That means electrons in the channel during the inversion. PMOS is P channel. That means holes in the inversion. And when you draw the circuit representation of NMOS and PMOS, you draw it something like this. Basically, this end is the source end of the PMOS. This is PMOS. This is NMOS. This is gate. These drains are tied together. Okay, and this is source of NMOS. These drains are tied together, but you call this as VDD. You still call this as VDD. Okay, and the direction of the current flow is in this direction. Arrow shows the direction. And this is something called as CMOS, complementary. I guess I have discussed it in some previous lecture. Complementary metal oxide semiconductor. Why complementary? Because these are complementary, opposite of each other. Here the inversion layer is holes. Here the inversion layer is electrons. And there is a problem because the the hole mobility is less than electron mobility. And because of that, the current in the PMOS, because you know the current equation has mu n C ox W by L. This is for NMOS, mu n. If you have to write the current equation for PMOS, you have to write mu P C ox W by L. Mu P is less than mu n. So that means ID for PMOS will be less than ID for NMOS. I mean, mobility is going to affect the current because holes are, I should say, heavier than that of electrons because holes are located much closer to the nucleus in a layman language. So they have more effective mass, hence less mobility, and hence in the PMOS you get a lesser current. And how do you tackle this particular situation? Because current throughout you have to have same current. So you solve this problem by playing with W by L ratio. This is the problem what circuit designers solve. Circuit designers mostly play with this W by L ratio. While designing the circuits, they tune this W by L ratio so that the overall current should stay same. Because they know the mobility is going to be different for the N and PMOS. Okay, so that is the question here. The drain current for PMOS is less than drain current for NMOS. That is absolutely correct. Because the mobility of the PMOS is less than that of NMOS. That is absolutely correct. So the statement 1 is true and 2 is true, and the 2 is the correct explanation of the 1. That is the overall scenario. Okay, and now question number 9. What is question number 9? Given this is substrate bias in a PMOSFET. Okay, that means it's PMOS. That means there are holes during the in the inversion channel, source to body bias must always be lesser than or equal to 0 for a PMOS. The source to substrate PN junction must be either grounded or reverse biased for normal transistor action. Okay, this is a very good question. That is what I wanted to discuss, but time didn't allow me to see. If you have a PMOS, that means this is N-type, let's say, and you have P plus regions here now. That's what I discussed earlier. That means during inversion there will be holes here. This is oxide, this is gate voltage. Okay, so this is body voltage. So these, I told you that these regions P and junctions. Oh, should be opposite. This should be opposite. There you have a PN junction like this. You have a PN junction like this, because this is N, this is P. So this is P, this is N. This is P, this is N. Okay. So I told you that these regions should be, these diodes should be reverse biased always, because we don't want the current to flow in these directions. Okay, you don't want that, you don't want current to flow here. You only want the current to flow in here, in this direction. So for that, the PN junctions must either, these must be either grounded or must be reverse biased in a normal transistor. When will this diode be reverse biased? When the P side will be connected to, let's say, a negative potential or lower potential, and this side will be connected to a higher potential. That is the only scenario it will be reverse biased. So we have to maintain that in order to make sure that this is a reverse biased transistor. So source to body bias must be always lesser than or equal to 0. That means this source to body bias, this particular, let's show it like this. This is V source to body bias with respect to the body. These two are grounded, so this should be less than or equal to 0. Okay, in order to make sure that these diodes are reverse biased. So that means if this is source region, P plus source region, source, and this is the PN junction formed here. This is the body. This is body. When you connect this to a negative terminal, you connect this to a positive terminal, you get this as reverse biased. It ensures that no current flows in this direction. No I flows here. Because you don't want the current to flow in the bulk or the substrate. It's waste. It's a power loss. And this happens in real circuits. Leakage current flows always in the substrate, and that plays a crucial role in losses. I should say that gives rise to very high loss of the power. So the statement 1 is true and 2 is true, and S2 is the correct explanation of S1. So somebody has any question? Somebody raise the hand. I will just finish the last question, then I'll take the question. Okay, so what is the question? It was asked in GATE 2014 that slope of ID versus VG of an N-channel MOSFET. That means it's NMOS. And they are talking about slope of ID versus VGS. That means they are talking about subthreshold swing, subthreshold slope. But they are not talking about it they are not talking about, I should say, log scale, because they have not mentioned the scale. So you have to assume it's a linear scale. So the slope of in a linear region is 0.02 per ohm. That means IDS versus VGS slope has been given as 0.02 per ohm. Okay, per ohm because it's I by V. It's per ohm is the unit of conductance. VDS has been given. For same device, neglecting channel length modulation. Channel length modulation we discussed. The slope of square root of D versus VGS under saturation is approximately. So you have a good question. Linear region, you have linear region of MOSFET where IDS versus VDS. This is the linear region. Ohmic, and this is the saturation region. So you are given slope here. You have to compute slope here. Okay, that's it. Now, you know in the linear region that current is basically equivalent to transconductance VGS minus VT. Anything we have to neglect? Okay, VGS minus VT times VDS. If you have to find the slope of this, how you find the slope? You differentiate it. dID by dVGS. And you that means you find dID by dVGS. What do you get? When you differentiate it, you get K times VDS, because this will be the differential of this particular thing will be VT will be 0. That's a constant because VDS has been kept constant. So differential of K VGS into VDS will be K times VDS, and this has been given slope. It is given as 0.02, but at VDS is equal to 0.1 volt. This particular information is given. What you get in is K, it will be equal to dou ID by dou VGS divided by VDS. What is dou ID by dou VGS is 0.02 divided by 0.1. You get approximately 0.2. So you obtain transconductance here, Kn, which is K. And now what you are going to do is that you are going to find in saturation. This was in linear. Now in saturation region, you have to write the current equation again. IDS is equal to, let's use the same, let's use Kn again, or K, this transconductance. VGS minus VT square minus VDS square divided by 2. Okay. Now, I think this overall should be like this. This is the overall equation. This is the current equation in the saturation region. Now you have obtained every other thing. But what you have to do, you square root both sides. That means this square will go. It will be square because you have to compute the square root of ID versus VGS. So square root of ID will be square root of K by 2 VGS minus VT. I think every other thing is given. Yeah, now you have to differentiate it. Dou root of IDS by dou VGS. It will be equivalent to, now you just have, you are left with this particular thing, square root of K by 2. And square root of K by 2 you found 0.2 by 2, you found it as 0.1, and this is approximately 0.3. So dou square root of IDS divided by dou VGS is 0.3. And why is this changing? So the typical range, okay. So the overall answer is basically 0.3. And I guess the accepted answer is 0.1, 0.2. Maybe there is some discrepancy in the calculation, but you will get the same thing. What is 0.
Yes, sir. This is correct, sir.
Is this correct? Because 0.2 by 0.1, 0.1. Yeah, this is correct. I thought I missed it. Yeah, so this is the overall, this is the actual answer of this question. So that finished up this session. Again, it took almost 2.5 hours. Oh my God. Yeah, please have these questions also featured in the recording, either this session.
Thank you, sir.
Oh my God. So somebody has so many questions. That is good actually. Please have these questions also featured in the recording, either this session or next. Is he here? Are you here, Ramaya SM, or you have left? Yes, okay, you are here. Then let me answer these questions one by one. I hope there is no any crazy question in this. Let me just read it one by one because there are so many questions. But it's good. I like to answer these. Why is the variation in ID with respect to VD in saturation more prominent for high VGS? Why is the variation in drain current with respect to gate voltage in saturation more prominent for higher VGS? Okay, let me draw it. Let me see what you are asking. Let me understand. So you are saying IDS versus this is IDS versus VDS. You have something like this. This is the linear ohmic region. This is VGS minus VT. So this is the saturation region. This is the ohmic region. Okay. So why is the variation in ID okay with respect to VD fine in saturation more prominent for higher VGS? Okay, more prominent. You mean to say this increases and with because VGS is increasing. That is obviously the case because if these are N plus regions, you have this as oxide, you have this as gate. You are increasing the gate voltage, you are inducing more electrons here, even though the channel has pinched off, but this is the pinched off channel. This is the pinch off overall channel now. And there are few electrons here, but you have induced more electrons here. And you see the band diagram is like this. Band diagram will be like this. Band diagram will be at very high gate voltage, very high VGS. The band diagram will be like this. It will be like this. This is source, this is gate, this is drain. And you see when you have induced so many electrons here, so many electrons here. Let me draw it exactly like the pinch off. So many electrons here. Some of the electrons at this particular position, they just rush down to the drain side because of the drift present, because of the huge drift, I should say. When does the pinch off occur? Pinch off occurs at very high drain to source voltage. Okay, so when the channel is pinched off, you have now more electrons. You see the current depends upon how many things. Current depends upon number of electrons, electronic charge, and area and drift velocity. This is the old textbook current equation from the class 12th, NAEVD. What are the things you can change in this current equation? You cannot change electronic charge. You cannot change area. What you can change is n and drift velocity. N is the number of electrons. You increase the number of electrons by increasing the VGS, you increase the current. As simple as that. Whenever the number of electrons increase, it gives rise to more current in this particular area. And also you're basically playing with this drift velocity, but this is the simplest explanation I can give. So
So
current
also
depends
doesn't
upon,
the slope change?
sorry?
Doesn't the slope also change, sir? When we increase VG for higher VG, the variation of
Yes.
VD,
Yes.
ID with respect to V.
Which slope are you talking about?
I mean, due to channel length modulation, we have
That
a
is what
certain slope.
exactly. That's what I mentioned in the earlier part of this lecture that actually this is not a constant thing. It should have been the constant like this, but there is a slope. This gives rise to output
Yeah, so
resistance.
will the slope change for higher VGS than for lower VGS?
Yeah, okay, that is the actual question. Yes, it will be higher output resistance.
Why would it be
It,
so?
it, it gives rise to output resistance because now you have more electrons in the channel, you have more electron scattering events, and that will give rise to a more electron resistance. Resistance is because of scattering. Current will definitely is
Oh,
current is definitely going to shoot up. It's going to increase. The as you It's like a knob. Voltage gate voltage is just like a knob. You turn the knob, you increase the current. You turn the knob again, you increase the current. But what you are going to see is that output resistance is also going to change. Early, this is like this is like this. You see that this particular slope is going to change accordingly. And this is something like dou I ds divided by dou VDS. This is the output resistance. Output resistance. It also comes into picture. But to the first order approximation, when we initially when we initially talk about it, we don't talk about these effects initially because of the output resistance. We usually consider that it Goes up, then it saturates. Goes up, then it saturates. But yes, you are absolutely right. That because of channel length modulation, it will take place. Okay.
Okay, sir. So
Um,
in that case, if it is flat,
Yeah.
we'll have a infinite resistance.
Yeah, infinite ways. Yeah, you cannot have. I mean, you cannot have a flat thing, definitely, right? You cannot have a
Yeah.
pure constant current source because in that case, the what will be the slope? It will be zero, and 1/0 is infinite, and resistance will be infinite. Correct?
Okay. So you
Sir,
mentioned the resistance is due to
scattering,
scattering events.
Yeah, resistance
But
is always because of scattering events.
okay, so
You
in that
cannot.
case, for a
Hmm.
constant current source, you'll have infinite resistance. That means scattering event is so high.
No, that does not. It does not mean the scattering events. Scattering is always present inside. The whole
sir,
fundamental thing.
scattering,
Yeah, yeah. Just let me complete. Yeah, you are saying something. Just now let
sir,
complete.
scattering is like that Feynman diagram, sir.
Arey, don't go into that detail right now. It's just a device course. Why are you including Feynman diagram here? It is because of that, but right now we're not talking about that. We're talking about electronics and from the pure electrical perspective. Let's not go into Feynman diagram right now. So you are absolutely correct. It's because of that, but his question is a little bit different. So let's not go into Feynman diagram. What I am telling him, what I am trying to make you understand is that scattering always is present. If this is the EK diagram, you remember from my previous lectures or previous sessions, this is the EK diagram. There will be a EK diagram at this point. Okay, at in this band structure, there will be this band diagram. Okay, E versus K. If you zoom it out here, what happens when the electron at this gamma point where K is equal to approximately zero. Let's not think about this gamma point or other things. When the electron goes here, there is some scattering center. It can be ion, it can be another electron, or it can be any positive charge, or it can be any negative charge, or anything. So what happens here? Electron reaches here, it gets into random direction. It changes its, I should say, randomizes its momentum. If the momentum at this position was k1, at this position is k2, so at electron reach here, let this momentum be k value be k3. So its momentum value has been randomized from k1 to k2 to k3. So that gives rise to basically the resistance. Why? Because because in the real space electron was like moving in this direction, but now because of scattering it's moving like this. It's scattered again, moving like this, and then this, then it moves here. And these particular events basically give rise to the resistance inside the material. That's why you don't have a pure, I should say, pure channel without any resistance. And that is why I brought the concept of something called as ballistic. Ballistic means if you make the channel so small that just one of this scattering event happens, or I should say whenever electron encounters another electron it gets scattered, but the channel length is so small of the order of the scattering length that electron directly goes into the drain. It does not even, after scattering, it does not even hit any other scatterer. It directly goes into the drain. That is something called as ballistic, where the resistance drops almost to zero. There is no resistance there. But we are talking here about diffusive transistors. Diffusive means the motion will be like this of the electrons in like a diffusion, a random motion, the random scattering events, which which randomizes the momentum of the electron. Okay, this K is basically associated with the momentum of electron. K is called as wave vector, but momentum of the electron is h bar times k, quantum mechanical. You have studied it in initial lectures. Maybe I might have discussed. H bar is the reduced Planck's constant times the k. And from Newton's equation, you can write force is the rate of change of momentum with respect to time. So you write it as h bar. H bar is constant, dk by dt. So if you have a change in the k with respect to t, you have the change. You have the variation of the forces. Okay. Now from this particular thing, you can basically compute any equation. Now you know the force from the Newton's equation. You can basically apply the Newton's law in order to compute the other variables, maybe the velocity of the electron, acceleration. You know the force now. You can compute even the acceleration, even the velocity of it, and that gives basically that's the fundamental thing behind the resistance. Hope that answers your question. What is he
Yes,
saying?
sir.
Like in solution state electrochemical current, which has sweep time dependent on current. In solid state also there is any dependency on sweep timing. What is that? Electrochemical current solution state. Man, I'm not a chemistry person. I'm a solid state person. Okay, let me just think about what it is. What it is. Like in solid state electrochemical current, which has sweep time dependent on current. I'm not able to get your statement. In solid state, there is also any dependency on sweep timing, voltage sweep speed. What is voltage sweep speed? Is it that how fast you are sweeping the voltage? Just like if you are applying the voltage like this, then you are sweeping it like a ramp. Is it that, or is it something else? Yeah, if you are doing sweeping the voltage like this, then there is a dependency of the current. And there will be definitely dependency of the current. If that is the meaning of the sweep. I don't know what you mean by the sweep exactly. So let me answer his second question. Why do we make source and drain N plus degenerately doped instead of just N doped? Okay, it's a good question again. I talked about it. Basically, you dope it highly because these are just like probes. Probe means you just connect two terminals here, and terminal is metallic, and metallic has to connect with this region. So in order for the regions to be similar to that of a metal, you dope it very high so that there is very little difference in the Fermi levels and the mismatch between a metal and a degenerately doped semiconductor. Because at the end of the day, you have to probe it. You have to connect the terminal to the MOSFET, and so that you can get the current out, or you can read the current or the voltage. So that's why you dope these regions very high in order to prevent that particular mismatch. And this particular concept is the metal semiconductor junctions, where you studied about the Schottky barrier and the ohmic contacts. Those concepts basically come here. Whether you are going to make a metal semiconductor contact as a ohmic, or whether it's going to be Schottky, it depends upon the doping. If this is metal, if this is semiconductor, you know that there will be something bending like this. If the bending is like this, it's a Schottky barrier. This is not preferred. Okay, we prefer the metal semiconductor contact to be ohmic, something like this. Oops, not like this. Where the conduction takes place by thermionic emission, or the IV characteristics are almost linear in certain regions. So that means it's an ohmic contact. You have studied that in metal semiconductor junctions. So that's why this particular region is highly doped for that particular aspect. Okay, because simplest answer is that you have to match at least I should say the Fermi level is for the highly doped, the Fermi level of the conduction band, the Fermi level of the semiconductor will be almost in the conduction band, just like what is the scenario with the metals. So you have a huge sea of electrons there. You have a huge sea of electrons. You have very good chance of connecting the electrodes with it. I hope that answers the second question. Why do we create N wells? Why do we create N wells for source and drain instead of just directly connecting the source and drain metal terminals directly to? Okay, that is the third question. Why do we create N wells for source and drain instead of just directly connecting the source and drain metal terminals? Why do we create N wells? Okay, that again answers the same question. Connect the, you cannot directly connect yeah, in certain scenario, you can actually connect the metal. If you, let's say this is a MOS. Let me drop this. This is MOS, just MOS. MOS, oxide. You inverted the channel here. Now you have to have something at these locations to take it out. You can take it, just connect the probes, just connect the terminal probes. But one reason is that you have to connect the first of all you have to connect the terminal probes here directly. That means you have to connect the metal. You have to make it metallic. Whatever idea is to make this metal, to make this metallic. If this is overall metallic, this will be highly conductive. Okay, you see that this is not feasible. Why? Because first of all, when you see these source and drain regions, they are the part of this p-type substrate. How they are made just by doping these regions highly. They are the part of this p substrate. If you make the entire thing as metallic, it will be conductive. You no longer have a control, and the current will flow throughout. You don't. That's why you we are having a PN junctions here, so that they can be reverse biased and the current only flows at this particular location. You don't want every single thing to be conductive. Okay, you don't want those pathways to happen, pathways to for the flowing of the current. That is one way of thinking about it. And the other way of thinking about is that whenever you make a CMOS technology, you connect another how you make a CMOS technology, that is PMOS plus NMOS. You integrate it by connecting another structure here and making the source and drain contacts, making this is metal oxide semiconductor, and these are the contacts here. There is a some layer of buffer layer to isolate these. This is P plus, this is P plus, this is N type, and these are holes, and there are isolation layers present here. So that is one another reason why do you kind of make these pockets, and these are just highly doped pockets in the same substrate. You don't connect a you don't connect a different source or drain to this region. These are the same part of a substrate, just you do something called as ion implantation. You inject very high energy dopants into that region, and you dope it highly so that resistance in those regions fall. They almost become metallic. Only those regions where the conduction can take place, and you have a good conduction. This is the overall schematic of a PMOS, CMOS actually, where you have both P and N type semiconductor. Okay, and why is enhancement type MOSFET called so? Enhancement means because you have to enhance the channel. Unlike in depletion, it's just the English word. You enhance the channel. Enhance means you create it, you modify it. Or rather, it should be a good word is like it. You enhance the channel by applying the voltage. That means you turn it on by giving the voltage. And depletion means you turn it off. You deplete the channel of the carriers. You turn it off by applying the voltage. That's as simple as it. When we connect negative voltage to S and positive voltage to D,
So that question got incomplete. I'll ask
oh,
in the next session.
you have to ask this question in
Just
in
in
this session.
okay,
You want to ask, then you
sir,
can
I'll
ask.
paste it. Just
Hello, sir. I was actually due to some internet issue, I didn't heard the answer properly. Like
What if you have
actually, when
static
I
loss
do
of
some
power?
IV measurements,
Hmm.
I will get some noise or some high current if I sweep very fastly,
Just a
and if
second.
I
Yeah, yeah.
sweep
Just
very
ask me, or just keep asking the question. I'm
and if
just
I sweep
moving.
very slowly, like it will come little less current or very connected path. But in solution state like electrochemical cells,
Hmm.
there some time dependence will be there. Like the peak current will change if we uh, sweep the potential very fastly. Like in solid state also, like in transistors, like it is that any cases there where sweep rate matters.
You're talking about the sweep rate of gate voltage, right?
Yeah,
Yeah,
to
sweep
study
rate is, yes, sweep rate is going to matter a lot. I'll tell you why. There is something called as there in even in the diodes there is something called as reverse recovery time. So that is the concept which says that there is some time required to, let's say you have a diode. Just give you a simple example. When you turn the diode on, you connect the positive here and negative here. So as a result of which the electrons go this side, the holes go this side. Okay, and the current starts to flow in this direction. So this is normally on diode. That means this is the circuit diagram of this. What you do, just remove this source. You suddenly turn it off. There is certain time associated with charges moving back to the N and the P side. So the charges take some time to move back to the respective sides when you move the applied potential. That means if in forward bias this was the case, just the barrier reduced. This is the forward bias. The electrons went here, the holes went here. When you remove the bias, it takes some time to form back this equilibrium situation. And during that time, these holes have to move back here and electron has to move back here. Only then this particular scenario can be established again. So this particular thing is called as recovery time, or this is called as recovery time of a diode. It needs time to recover. The charges takes time to recover, go back to their initial positions, and then move again, come back again. Okay, so that particular time basically reflects in if you sweep the voltage. If you sweep it much faster, if you sweep it much faster, or you turn the diode on and off much faster, you will not you will not be able to follow the voltage accordingly. Let's say if you give a sinusoidal voltage at the input and you at the output you expect the sinusoidal voltage, but maybe due to some reason you get a voltage output like this. It clips off the voltage. It clips off these particular ends, and that may happen because of this particular scenario, that the diode is not able to follow the voltage change you have applied. That is what I guess you mean by sweeping. So yes, it is necessary that you sweep at the particular rate. You got the concept? Hello, Hemant, you got the answer of this
Hello?
question.
Yes, sir, I got it.
So you are right. The sweeping is necessary. Obviously, that is going to be necessary in all the cases. At what rate you are going to sweep the gate to source voltage, or in case the voltage in the diode. That's why in the diode circuits, whenever you study the diode circuits, you study about clippers, you study about the clampers, you study about these are the analog electronics topics. You study about those particular things. You study about that when the voltage will be clipped and other things. In terms of you study about something called as reverse recovery times of a diode. What happens when the charges have to move back, whether the current is able to follow or not. Sometimes when you give let's say you give a square voltage to a diode, let's say this is current versus time. You expect this is input. You expect the output to follow the same, but you get the output to be something like this. If this is let's say if this is a diode, it will not conduct in reverse bias. Then you should get only these particular paths. Okay, but you get something like this. These peaks come because of reverse recovery time. These peaks should not have come because यहाँ पे डायोड फॉरवर्ड बायस है इन पॉजिटिव रीजंस में, बट यहाँ नेगेटिव में रिवर्स बायस था. रिवर्स बायस में डायोड डज नॉट कंडक्ट, but you see these peaks These these peaks appear because of reverse recovery time, because it takes some time for the charges to move back to their original positions, original locations. That 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 gives rise to this particular, I should say, impulse of this current in the negative direction. That is the actual concept. So yes, you are right. And what else was the question? Okay, do you have a?
So, sir, if I give a step-like potential like 10 millivolts, 20, 30, like that,
Hmm, hmm,
um, yeah, is there any difference if I directly give from 0 to, let's say, 100 millivolts, is strong? Like whether any destructive process will happen, like there is filament kind of channel will form, is and it like some channel will be enhanced in that case, like we are creating a path. Is there anything like that happens? Because there are some device like this neuromorphic and resistive switching,
hmm, hmm.
uh, it will forms a filament in the
That
this
is a
interface.
that is basically a different concept. What they use in the neuromorphic device, what they use, that particular thing is wholly based on the process of formation of filamentation, where you have, if you have a, if you have a oxide, and if you have, let's say, this is gate and this is semiconductor. In neuromorphic devices, they apply some voltage here, and they want the current to flow in this direction, because what happens because of the application of the voltage there, you get formation of something called as filaments. There are some conductive pathways inside the oxide, which atoms both closely, they come so closer to each other that they form a filament like this, and current starts to flow in that filament region. Okay, that is a different process. This should not happen in the MOSFET. This is a very degrading, I should say, scenario for a MOSFET to happen. It cannot happen in MOSFET in any scenario. Oxide is not allowed to conduct in a MOSFET, at least for the CMOS operation, for the operation we want.
Okay,
Okay,
so in dielectric of CMOS, it is very rare to happen.
it is rare to happen, at least if you, I should say, what is called as, don't apply very high voltage of the order of breakdown of that particular oxide. Every oxide has a breakdown voltage. It may depend upon thickness, it may depend upon the uh, absolute, it may depend upon the permittivity of that oxide, epsilon value. That determines the breakdown value of that oxide. Second, there is something called as negative by no there was a concept called as time dependent breakdown. There is something called as time dependent breakdown. With time, when you use it for a longer period of time, what happens is that the oxide can cause leaky currents to flow. It's a very open research problem, even still, time dependent breakdown. And that can give rise to currents, but it happens with a very, I should say, large period of time. It does not occur as such in the devices because it is very detrimental effect. Why detrimental? Because it will cause the capacitive action to lose, because if charges start to flow through the oxide, the charge will reduce, the capacitance will reduce. The capacitance is the major factor in controlling the channel. If there is no capacitive action, if there is no charge at the metallic plate that stays there, it cannot induce the opposite charge in the channel. Okay, that is a very degrading factor, and you cannot control the channel even. That's not going to happen. So that is the overall
So is
scenario.
there a way to control this leakage current? Is it like the tunneling current only?
Yeah, it can happen because of tunneling. Yes, it is mostly because of tunneling, I should say. Even at if there is a, if there is a metal, there is an oxide, there is a semiconductor. Let's say if there is a semiconductor like this, then these bands are bent like this. This is the oxide. Then Yeah, then if you go on increasing the gate voltage more and more, the bending will start to increase more. So even this bending will be huge, and this bending will be like this, and this will be so huge bending that this appears like a very thin barrier for the electron. Now this appears like a triangular barrier. This region is like a triangular barrier for electron, and electron as a wave can tunnel through it and appear on the other side. So this is called as tunneling breakdown, and that mostly happens in the. I mean, this is one of the reason for leakage currents. And if you have a tunneling barrier like this is an oxide, and if you have a metallic layer on it, a metallic layer on the other side, and if you have a semiconducting region on this side, the electron can basically tunnel through this triangular barrier, basically exponentially decay, then appear on the other side. This is the wave function of the electron. And if you have another scenario, that if you have this triangular barrier but electron can tunnel here instead of in the triangular region, this is if it tunnels in the triangular region, this is something called as Fowler-Nordheim tunneling, and this is called as direct tunneling. What happens in Fowler-Nordheim is it goes into the electron tunnels and goes into the conduction band of oxide. This line is here, this is the conduction band of oxide. But in here, direct tunneling, it directly tunnels through and appears in the other side. There are other scenarios, maybe, but for that, those are very, I should say, specific problems which has some specific quantum mechanical solution.
Okay, sir. Thank you. One last question. Like,
Yeah,
is it possible to use this NDR effect, that curve also in switching purpose? Like the regime
which
of the showing positive current, positive slope, and it has negative slope at one particular point. Is it possible to
say it
use that
again.
effect as
I didn't get your question. Say it again.
like NDR effect that at the very beginning bias voltage, we will be
What is
having
ND? What
some
is what is NDR effect?
that negative differential resistance. Like
Okay, okay.
one peak will come and the current falls down and again current rises normally. In that small regime also we can use it as switching purpose. Is it?
That is used in the neuromorphic devices for the switching, the negative differential resistance, uh, where you have the current something looks like this, but when you turn it on, but when you turn it off, it's not able to follow its path, and it forms like a resistive state. So you call that as high resistive and low resistive state, right?
Yeah, yes, sir. But in PN junction also they will draw at a very beginning small voltage. There will be some NDR effect forms, which is in a very small bias range only.
In
Is that
PN junction.
yeah? Like in metal semiconductor junction also, it forms a small NDR effect
At which region?
at very in forward bias only. Very before threshold voltage only, it will rise and it will fall down.
You're
Yeah,
saying here.
in that region. Yeah, I read
Okay.
in one book of in Puri Babbar book that they mentioned a small um, positive slope, and then it will having negative resistance by negative slope, and it will normally
Why
stop.
that happens?
Like the this energy level matching, the Fermi level of the electrode will come very near to it, so it will conduct, it will transport it. But as we apply voltage, the difference will be bigger, significant, so the current will reduce. And like resonance tunneling, I think in resonance matching of wave function, it will
Maybe
first will
I'll
show.
look for it. I'm not able to think properly how this is going to happen, because resonant tunneling is a different concept. But in a PN junction, how this is going to implement, maybe I'll look for it. Okay. Thank you for this
Okay, sir.
question.
Yeah, I will try to send you that picture
Okay,
also.
sure.
Uh,
Sure. Thank you.
thank you.
Any other question anyone has?
Thank you, sir.
Okay, fine.
So I have
I think
asked
I
two
should
more
be.
questions. Which are,
Yeah, you have a question. Where is the question? Okay,
yes,
when
sir.
we connect the
One and two.
negative voltage,
Yes.
okay. When we connect negative voltage to S, positive voltage to T, the bulk source region depletion region is reduced, and we have electrons being injected from source to the channel. Why don't we have electrons being injected through bulk instead of just being close to oxide semiconductor interface? Okay. So it's quite comes from the electrostatics, I guess, what I've understood from the question. Uh, when we connect negative voltage and to when we connect negative, okay, this is negative. Let me understand your question. Positive, fine. The bulk source depletion region. The bulk source depletion region is reduced. The bulk source depletion region. Okay, you mean this. Okay, this is positive. Let me draw it pictorially. Okay, and that this gets increased. Let me draw it to visualize. We have electrons being injected from source to channel. Okay, this is electron injection. Fine. Why don't we have electrons being injected to bulk instead of just being injected to source? Correct. You are absolutely correct. That happens. Electron can get injected through all these pathways. That is the actual concept I was telling you. Because these are pockets like a curved Gaussian pockets, electron gets injected throughout, but they cannot flow in these regions because these are reverse biased p-n junctions. That's why the reverse bias is necessary. In the reverse bias, you don't have the current flowing, you don't have the electrons flowing. So most of the electrons flow and they stay in this region because this is a conductive pathway. And because
So
and
that means if
because and
electrons. Okay.
let me complete. And because you have applied a gate voltage, you might have applied positive gate voltage, and positive plates are going to attract those negative electrons towards the oxide, and they are going to stay at a layer close to the this interface because of the electrostatic coupling between the capacitive coupling between the gate electrode and the channel. They stay close to the oxide. In fact, they form something called a surface charge. It's almost like a surface charge, layer of charge.
Okay, sir. So
Okay,
wherever they get injected, they will be drawn close to the channel.
exactly. But yeah, they get everywhere. They are electrons. They wherever they. I mean, if they are getting injected here, they are getting injected throughout in a three-dimensional scenario. But because there are non-conductive pathways, electron likes to flow through a less conductive pathway. Now, it likes to flow through the less conductive pathway, and it does not like to go through the higher conductive pathway. In fact, if some of the electrons may leak even in reverse bias, you know that even in reverse bias, some of the current flows, reverse leakage current. That basically gives rise to the leakage through the bulk through the substrate, which is a very detrimental effect. It's not usually good. That is why sometimes we also apply the bias here, something called as body voltage. My pencil is down. Body voltage you apply sometimes to repel those electrons back to the channel. ठीक है? Even if some electrons go towards the
Okay.
body, you apply such voltage at the body that they get repelled again towards the surface and stay near the channel. That is the thing used basically in the devices right now. We apply the body to source voltage, something called as body effect, that actually affects the threshold voltage also. थ्रेशोल्ड वोल्टेज को इफेक्ट कैसे करेगा बिकॉज नाउ इफ यू अप्लाई एनी वोल्टेज एट द बॉडी those electrons get repelled from the substrate towards the channel. Now already you have electrons near the channel. Now you have to apply lesser voltage at the gate terminal to induce the channel. So that affects the threshold voltage. As simple as that. Hope that answers your question.
Yes, sir. There's just one last
Okay.
question, sir.
Oh God, it's 9. It's been 3 hours, man. Okay. Let's just
Sorry, sir.
last question. Okay, okay, just last question. I'm feeling hungry and my pencil is down. I cannot write anymore.
The second question, sir. I already posted it.
Why do we have static loss of power in depletion type MOSFET? Ah, okay. Static loss of power. Mm, okay.
You told that we already have a channel, but why does
Mm-hmm.
it contribute to a power loss?
Okay, let me think about it. Why should it? If let's say we have a transistor, we have not connected any of the supply to it, then yeah, let's say you have not because the power you I should say apply at the gate terminal, that mostly gives rise to the or rather the I should say the power voltage you apply at the drain to source terminal, that makes the current to flow. And now even if you have zero gate voltage, ideally you should have zero current. But in these type of transistors, the current will not be zero, because even if the gate voltage is zero, because there are already channel in the channel formed in the depletion type mode. And as a result, there will even if the small voltage is present between the gate and drain terminals, the current will start to flow. And the current flows means the P equals I square R losses will be still there, even if there is no gate voltage at all. So there is a conductive pathway always. You don't want that conductive pathway to be there. You just want it to be empty, so that if anything is present at the drain to source terminals, anything is present at the drain to source terminal, it will not conduct if there is no conductive pathway. And that is controlled by the gate voltage. That is why gate voltage is necessary in order to induce the channel. Once the gate voltage induces channel, conduction can take place. But once the gate voltage is removed, the conduction should stop. If there are already carriers present in the channel, the current is going to flow through the drain to source pathway without the gate voltage. That is going to be causing the I square R losses, and that's going to heat up the device even. Does that answer your question?
Okay, sir. Yes, sir.
Okay.
Thank you very much, sir.
Okay. Good questions. Fine. It's been a very long session. So, anybody has any other question? So now it has already passed 3 hours, so doesn't matter to
Thank
me
you,
now.
sir.
Okay.
Thank you, sir. Good night, sir.
Good night. I'm, I'll have the dinner first. So, what's your name, Ramaya? Where are you from exactly? What are you studying? Just let me end this session.